Ladies and gentlemen, dear colleagues, I am glad to welcome you in Taras Shevchenko National University of Kiev. I would like to introduce the Vice Rector of Taras Shevchenko National University of Kiev, Professor Sergei Vyzhva, for a welcoming speech. Sergei Andreevich, please.
Шановні учасники 6-ї міжнародної конференції «Фізика Рідин. Сучасні проблеми». Радий вітати вас від імені багатотисячного колективу Київського національного університету імені Тараса Шевченка, особисто від імені нашого ректора, з початком роботи нашої конференції. Цього року всі події, які відбуваються в університеті, присвячені 180-й річниці утворення нашого університету і 200-й річниці від дня народження Тараса Шевченка, ім'я якого присвоїв наш університет.
Respected participants of the FIX International Conference, Physics of Liquid Matter, Modern Problems. I'm glad to welcome all of you on behalf of the authorities of the Kyiv National University, especially the Rector of the University, Academician Dubetsky. And I would like to say that this year all events taking place in the university are devoting to 180 years from the day of the foundation of Kyiv University and 200 universities of famous Ukrainian poet Taras Shevchenko.
Цю конференцію ми організували і проводимо разом з Інститутом теоретичної фізики імені Боголюбова Національної академії наук України. Я радий бачити сьогодні в цій залі вчених з багатьох країн світу, зокрема Бразилії, Грузії, Канади, Китаю, Марокко, Мексики, Польщі, Росії, Сполучених Штатів Америки, Таджикистану, Франції, Швеції, України.
This conference we organized together with the Bogolyubov Institute for Theoretical Physics of the National Academy of Sciences of Ukraine. I am glad to see in this hall many scientists from various countries, especially from Brazil, Canada, China, Georgia, Germany, France, Morocco, Mexico, Poland, Russia, Sweden, Tajikistan, United States of America, Ukraine.
Ознайомившись з програмою конференції, слід констатувати, що ваша конференція має не тільки фундаментальний характер, але й значний прикладний. Сьогодні ви робите новий крок до створення новітніх технологій у медицині, промисловості, ядерній енергетики і інших галузях промисловості.
Becoming familiar with the program of our conference, it is possible to state that this conference has not only fundamental, but also practical and applied character. Today, we undertake a new step to creation of numerous technologies in medicine, industry, and nuclear energetics.
Історичний досвід говорить нам про те, що наука завжди об'єднує народи, бо по своїй суті вона є інтернаціональною. Ще підтвердження, чому ми бачимо серед присутніх в залі. Я впевнений в тому, що ваша зустріч на конференції дасть вам можливість обмінятися думками стосовно існуючих наукових проблем і не тільки цього.
Historical experience tells us that the science can also always unify nations, because on the essence it is international indeed. The proof of this statement we can see in this large and interesting unique conference. I am sure that our meeting at this conference will give you a happy opportunity to exchange opinions concerning existing scientific problems and will help to increase mutual understanding between peoples of your countries.
Бажаю успіхів вашій конференції і щастя кожному з вас.
I wish great successes to your conference and personal happiness to each of you. Thanks.
I would like to introduce the Vice President of the National Academy of Science of Ukraine, academician Anatoly Zagorодny, for a welcoming speech. Anatoly Glebovich, please.
Thank you. Good afternoon, ladies and gentlemen, and dear colleagues. It's a great honor and pleasure for me to welcome the participants of the 6th International Conference on Modern Problems behalf of the National Academy of Sciences of Ukraine and the Bogolyubov Institute for Theoretical Physics. Taras Shevchenko National University of Kiev and the Bogolyubov Institute for Theoretical Physics have a long-term tradition of collaboration in the fields related to the scope of the present conference, and that is why we decided to organize this conference together. Many scientists from the university and the Bogolyubov Institute contributed considerably to the progress in condensed matter physics, in particular in physics of liquids, and it's sufficient to recollect prominent scientists such as Professor Davidov, Professor Yukhnovsky, Professor Shimansky, Professor Golin, who founded powerful scientific schools in the field of condensed matter physics. Now this secondary school continue to deal with studies initiated by their teachers, their founders. And I am glad to know that one of such schools on liquid metaphysics is headed by Professor Bularin. Dear ladies and gentlemen, dear colleagues, all of us understand that the present time, in view of the general situation in Ukraine, the present time is not the best time to organize scientific conferences in Kiev. It was necessary to be sure that we can collect a sufficient number of speakers and participants, but I'm very glad that today we have more than 100 participants from about 10 countries, so our doubts have been in vain. I'm sure that I believe that our conference will be useful and interesting for its participants. So let me wish you to have a very successful conference, brilliant talks, fruitful discussions, and all the best. And I also like to wish our guests to have a nice time in Kiev. Thank you for your attention.
I would like to introduce the representative from the International Advisory Committee, Professor Michel Ravizon, for a welcoming speech. Michel, please. Professor Ravizon, please.
Thank you for this welcoming. First, I would like to correct you, dear Professor Bularin. I am not professor. Sorry. I am only researcher. In French, you know, it's similar to the Academy of Science here. I am from the CNRS, so in French, Centre National de la Recherche Scientifique, in English, National Center for Scientific Research. I am coming from a small city, but very well-known city, Strasbourg, which belongs to a small land. Sometimes this land was German. No, this land is French, you know. So there are some nature, and I like that. In my lab, first, CNRS own laboratory, which is also associated with the University of Strasbourg. This lab was created just after the Second World War for research in the polymer science. And the great scientist of this lab was Henri Benoit. But this lab has been built by Charles Savin. And of course, our lab has a debt with respect to De Gennes, a great theoretician who was in Paris. So first, it's a pleasure to be here for distinct reasons. I cannot give you the list, but I wish to thank Professor Bularin for his invitation. Like that, I plan to present you some results, new results on polyelectrolytes, a special liquid. And also, I would like to to be grateful for respect to Professor Buladin. Why? Because we have built together with some other person like Natalia Pisomon and also Isabelle Boudou and Rodolfo Jalabert, a common master in between Taras Shevchenko University and Strasbourg University. And this common master was a little bit difficult at the beginning, but it seems now to work. Unfortunately, I have almost finished my career. So. Also, I would say that thanks to Professor Buladin, I have met some students from your university. At the beginning, I was a little bit angry because I believe I thought that it was a little bit too risky, but it's not the case. They are very good, and the last ones are perfect, really perfect. They are first in the Master 2 at Strasbourg in physics. So, that's all. Thank you again, Professor Buladin, and I wish you a successful conference. Thank you very much.
Thank you, Professor Ragizo. I would like to invite Professor Charlie to chair our plenary session. Alexander Vasilevich, please.
Thank you very so much, Mr. Buladin. And it's my great pleasure to introduce to you the first speaker of our plenary session, Professor Mikhail Anisimov from the Maryland University Institute of Physical Science and Technology, United States of America. Please. The duration of our lecture is 45 minutes, 40 minutes for lecture and 5 minutes additional for questions.
Just, can you hear me? Ladies and gentlemen, good afternoon. It's my great pleasure and high honor to be the first speaker at the conference. I visited Kiev first time exactly 45 years ago, in May 1969, after graduation from Moscow State University. Since that time, I have developed wonderful friendship and collaboration with my Ukrainian colleagues, not only from Kiev, but also from Lvov, Kharkov, and Odessa. I would like to dedicate my talk to all of them. Thank you so much. My talk will be about supercooled water. This is now, it is very cold water, but it's a very hot subject. The more and more papers and experimental, theoretical, and computational research indicates growing evidence that maybe in deeply supercooled water, just below the line of homogeneous ice formation, would be a liquid transition when water separates into different waters, the same H2O, but two different arrangements of hydrogen bond network, which make water diffusion and gives an example of so-called liquid polyamorphism, existence of two species, single liquid substance in two different liquid forms. Before I start talking about supercooled water, I really want to acknowledge and thank my members of my group, especially people who contribute in this research. In particular, I can show my postdoc, Vincent Holten, from the Netherlands, from Poland, Dutch, John Biddle, student from the University of Maryland, theoretical physicist, from the United States, is now at Yale, also postdoc for my former student in India, and Daphne Fuentilia, also graduated PhD. And these two people are not students. We are emeritus professor emeritus from the University of Melbourne, my close colleague Jan Sanders and his wife Annika Sanders from the National Institute for Standards and Technology. Okay, thank you. Next, please. Water. Everybody understands these two phase diagrams for ordinary substance and for water. They look very, very similar. You immediately can recognize the difference, which is very important difference, that the melting point for water has a negative slope, unlike most other substances. It is related to anomalous properties of water. Actually, this is essential. But not only that, please, next slide. Water could be supercooled, actually amazingly deeply supercooled. For example, for the pressure, this is a melting line, equilibrium thermodynamic melting line between water and ice. Ice could be in different forms, but this is not the point today. Most importantly, that, for example, for 200 megapascal, which is 2,000 atmospheres, water could be liquid in a huge range, 90 degrees. Even at ambient conditions, we could supercool water until the homogeneous ice nucleation, and unfortunately in bulk water, experimentalists cannot penetrate through this line because spontaneously water, supercooled water, metastable water crystallizes. But still, it's a very, very low temperature. Next slide, please. First time, to my surprise, the discovery of supercooled water was done many years ago. This scientific paper published in Latin by Fahrenheit in 1724, almost 300 years ago, where Fahrenheit reported on supercooling almost to minus 10 degrees Celsius relatively easily. Next slide, please. Supercooled water exists in nature. In high level atmosphere, microdroplets of water in clouds could exist at low temperature as low as minus 37, 38 degrees Celsius. This is a big problem, by the way, of spontaneous formation of ice, of supercooled water, not just water at 0 Celsius, but at very low temperatures. When the aeroplane is traveling at the height of 12 kilometers, could be ice formation or icing, which is a real practical problem. So the knowledge of properties of supercooled water is really important for, not only for science, but also for engineering. Next slide. Now, water looks when experimentalists dealing with water, immediately they recognize the water is the same substance, but two very different liquids. A liquid at high temperature, especially close to the critical point of vapor-liquid transition, and properties near 0 Celsius, and especially in metastable state, below 0 Celsius, dramatically different. Next slide, please. First reported density of supercooled water was also a long time ago, almost 200 years ago. Next slide, please. And this property indeed shows that the water is anomalous. At 4 degrees Celsius, the density of water exhibits a maximum, And upon further cooling, especially to metastable region, the density goes down, unlike ordinary substances. And 200 years ago, 100 years ago, of course, the supercooling was not significant, but now we have dramatic decrease of density, which shows that maybe the derivative of the density with respect to temperature could even be negative infinite. Next slide. If we look to the properties of hot and cold water, indeed we can recognize immediately that water is two different liquids being the same species. This is a dielectric constant of water, which is, for vapor deposits, near 1. At the critical point, it is about 5. And if water would be normal liquid, the blue line would never go to 100. It will just arrive maybe at about 15. But because water becomes a very different substance with developed hydrogen bond network, the dielectric constant goes up, and in supercooled region, it becomes greater than 100. Some people, in Russia, people sometimes have some scientific fantasies. Some people even speculate that maybe there should be divergence of dielectric constant and the water becomes ferroelectric. Who knows? But there is a lot of huge area for speculation today at this science. Next slide. And especially if you look at the heat capacity at constant pressure, it is also dramatic picture. You have, of course, divergence of the heat capacity together with compressibility near the liquid vapor critical point, but also you have near, like apparent, or at least possible, almost divergence, or at least very sharp peak of heat capacity at low temperature in liquid phase. So this picture opens the way of speculation that maybe the entire liquid state of water is just a narrow domain between two critical points. One a liquid vapor critical point at high temperature, and some kind of a critical point at low temperature. Next slide, please. Indeed, more than 20 years ago, in famous school in the United States, at Boston University, in group of Eugene Stanley, who is famous in his works in many fields of statistical mechanics, and in particular on water. His student, Peter Poole, and together with other members of Stanley's group, Stanley, made a wonderful and provocative and exciting hypothesis, just hypothesis or speculation, that maybe the anomalous behavior of supercooled water is associated with the existence of the liquid critical point in supercooled metastable state just below the line of homogeneous ice formation, thus not accessible for bulk experiment, but still this critical point, the virtual critical point, is responsible for all anomalies of water, and this critical point terminates the first order liquid, first order transition between two liquids at certain pressure, at certain temperature. And below this pressure, there is a continuous transformation from one kind of water to another kind of water without any phase transition, just like transition between gas and liquids around the critical point. Unfortunately, there is no direct evidence of this critical point in real water. I will talk about models a little bit later. Not direct evidence because this critical point and liquid-liquid phase transition above the critical pressure is not accessible for experiment. But there is a number of experiments, and I hope Lars Peterson maybe will today explain them more. There is a number of experiments which strongly suggest that this could be the case. And we may also want to say something about this. In particular, I was fascinated when I started thinking about this, because before I deal with the phase transition script phenomenon for almost 50 years, but I never actually thought about liquid water. But when I learned about beautiful experiments of Chinese experimentalist Osamu Mishima, I started believing that indeed could be the phase transition, liquid-liquid transition in water. Mishima started the melting lines not just of normal of water with normal ice, but also with ice polymorphs. And ice polymorphs, this melting line does not recognize the line of homogeneous nucleation. And this line, this supercooling could penetrate below the line of homogeneous nucleation. And he looks like at certain temperature, the melting line makes a sudden change in the slope, indicating that could be some change in the liquid phase. And when he did it for very low pressure, at ambient pressure, there was no such a change on the slope. It was a continuous change of the melting line. And he interpreted this fact as a possibility of the liquid-liquid transition along this red line, which terminated at the critical point of liquid-liquid equilibrium. Next slide. Okay, now let me come to some kind of speculations, still speculations, of why single component, pure liquid water, could unmix and exist in two different states. Jim Stanley, when I was in China as a guest of Professor Rene Shu, just a month ago, it was just a month ago, and Jim Stanley also was there, and he suggested a nice wording for the existence of two structures of water like Argentinian tango. And if you look at this picture, the pair in Buenos Aires could dance in being in different relations with the partner. In particular, it could be in water could be configuration of water molecules connected by hydrogen bonds in this way, or could be in more fragile way, which still could arrange hydrogen bond structure with lower entropy, high order, but smaller density. Next slide, please. So indeed, we're using, and next I will talk about the idea of two-state structure of water. Two-state structure not important at high temperature, but becomes more and more important upon decreasing temperature, and in particular, the maximum of density. One structure force normal water, force density to decrease when you heat the water, and another structure just opposite, like ice, density decreases, and competition between two structures is a result, the reason for the maximum of density at 4 degrees Celsius. So very simple idea. So we assume that there is a chemical reaction, quasi-chemical reaction, between two structures, A and B, in cold water. And the order parameter for this process is the extent of reaction, or fraction of low density component. The reaction constant, or logarithm of the reaction constant, is the thermodynamically conjugate to the extent of reaction, and it serves as the ordering field for this transition. So the assumption that cold water is a mixture of two alternative molecular configurations, A and B, high density, high entropy A, low density, low entropy B, fraction of each state is controlled by thermodynamic equilibrium. We cannot just extract one structure and replace by another structure with a single component, substance, single species. But pressure and temperature control this equilibrium. These two states may or may not separate. If these two states, two structures, form an ideal solution, it will not separate. Like a mixture of cyclohexane, which could exist in two forms, the saddle and the chair, controlled by chemical reaction between two structures. They form ideal solution, and liquid cyclohexane never separate. But phase separation may occur if non-ideality becomes strong enough to overcome the entropy of mixing, ideal entropy of mixing between two structures, like in this solution. Both high-density liquid and low-density liquid, they both contain A and B, but in different proportions. The lower the temperature, the more and more water contains low density, low temperature fraction. And most importantly, no global symmetry change across the Widom line. Widom line is continuation of the phase transition line into homogeneous region, like critical isochord in liquid vapor transition. And there is no symmetry change. We can go from one liquid to another liquid without phase transition. Next slide. This is not my invention, two-state model. Surprisingly, when I started looking at the literature, and immediately somebody told me that Röntgen, X-rays, was responsible for such state. But even before Röntgen, Harold Whiting, in his PhD, defended in 1884 already said that water could exist in two different states. Next slide, please. I will not show any formulas or mathematics, but I cannot miss one slide with thermodynamics. And for those who are familiar with thermodynamics of mixtures and binary solutions would immediately recognize this is just college level thermodynamics. So in thermodynamics of mixtures, the phase liquid-liquid separation between two components could be, in first approximation, described by two models, a regular solution and a thermal solution. In the regular solution, the ideal entropy mixing, which represented here, which is the same as ideal entropy of ideal gas mixture, competes with the energy of separation, with W being the interaction parameter, and if W is positive and strong enough, W defines the critical temperature of this phase separation. This approximation is known as the regular solution approximation, very, very simple. But also could be another possibility of phase separation, so-called a thermal solution, when ideal entropy of mixing competes with non-ideal entropy of mixing, and energy of mixing plays no or minor role. In this case, separation is also possible, and it is entropy-driven, not energy-driven like van der Waals fluids or most substances, but entropy-driven, like solutions of, for example, solutions of polymers. In this case, the critical pressure is defined by the interaction parameter omega, but critical temperature can be found from the condition of chemical reaction equilibrium through the chemical reaction equilibrium constant. Next slide. We applied two-state model to the properties of real water. I remind again that I don't want to be accused of unnecessary speculation that the critical point is not accessible. So the line of homogeneous nucleation shown by this brown dashed line prevents to go closer to the predicted phase separation between two liquids with the critical point. But real properties measured very well with high quality by many people. We have all available experimental data from around the world, statistically analyzed. They show that this model beautifully can describe and consistently all properties available today for bulk water. In particular, if you look, this is density as a function of temperature at different pressures, but you can also see the red line, which is the line of maximum density, which starts with 4 degrees Celsius and goes down, down, down to higher temperature. This is a red line, but also you can recognize grid line, and grid line is the line of constant fraction of low density water. In this case, it is 12%. So, roughly speaking, the maximum of density corresponds to a certain fraction of low density structure of water. And competition between two structures creates this density anomaly. This is a derivative of the density, so-called expansivity. You see the expansivity looks divergent at the critical point very strongly, according to the theory. And also data are limited, but at least they describe. Next slide. This is heat capacity. Heat capacity more controversial because there are many data. They're not exactly the same. So we need to have a compromise which is very close to the classical Angel data of Angel in 80s. But the red line is just prediction of the two-state thermodynamics. Next slide, please. Compressibility at different pressures. I think it's very reasonable, very convincing comparison. Next slide. Okay. So it was real water. Now, the first question which arises everywhere who deal with today with thermodynamics and statistical physics of condensed matter, what about simulations? There are many beautiful models of water. They're not perfect, they're different, but they're beautiful, and there are very accurate simulations available today. What about models of water? We analyzed at least 2 models of water, most popular. One is so-called MW water, atomistic water, the water represented just by a single atom. No charges, nothing like that, which could exhibit tetrahedral orderly. It is a popular model developed by Valeria Marinera from the United States. It is called MW water. We analyzed with our thermodynamics this model. Beautiful and very accurate simulations by Chandler and Lieber from Berkeley. And we, to our surprise, and also by Valeria Marinera, we found there is no liquid-liquid phase transition in this model. The model beautifully explains simulation data, but you see, in particular, density and compressibility and heat capacity and expansivity, while exhibiting anomalies similar to real water, they never reach divergence, so they never reach the critical point. We concluded that non-ideality of these two structures for this particular model is not strong enough to cause the liquid-liquid separation. Next slide, please. What was really beautiful for this model that Valeria Marinera directly computed low density fraction of low density fraction. In our case, this is the order parameter or extent of reaction. It is additional information in addition to response functions like heat capacity, compressibility, or expansivity. And in this case, we understand now why this model doesn't show phase separation, why non-ideality is not strong enough. The entropy of mixing almost zero, like between entropy of mixing of two polymers with large degree of polymerization. If you take two polymers and try to mix, there is no driving force to mix two polymers because the molecules are too long. The entropy of mixing suppressed by clustering, by degree of polymerization. Valeria Molinera also computed clustering in this model, and she showed that this model exhibits strong clustering. The water, this model of water, becomes like a polymer. Next slide. Next slide. This is computation of Valeria Molinera. Could you show the previous slide? Of MW water. You see that the points at different pressures. The dashed line is the bottle, and solid line is our thermodynamics. They are reasonably corresponds to each other, and they show that if you have a critical point, then this line, these are all the parameters, would have a vertical slope at the inflection point, and it never becomes very strong enough to have phase separation. Next slide, please. But there is another wonderful model, so-called ST2 model of water, also known as a Stellinger water, developed first by Stellinger a long time ago, which more detailed model of water, which indeed account for different charges and their interaction in water molecules. And this ST2 model of water exists in two different forms, and these both forms of ST2 model does show the liquid-liquid phase transition and the critical point. We applied our thermodynamics two-state model, or two-state thermodynamics to this water. This is density, and this is temperature. This is energy versus pressure. All data very beautifully described by our thermodynamics and support the conclusion of the authors who did these simulations, in particular Peter Poole, Eleni Deti, and Panagiotopoulos, and Jeremy Palmer, that indeed in this particular model of water we have beautiful confirmation of liquid-liquid transition. The liquid-liquid transition in this case energy-driven, not much entropy-driven, so this is almost classical case for the regular solution. Next slide, please. This is a computed order parameter for the ST2 model. For two versions of the ST2 model, in both cases, the quality of computation is not exactly the same, but definitely undoubtedly that the order parameter changed strongly enough with a very large slope near the critical point, like the critical isotherm near vapor-liquid transition, similar. And the jump of the order parameter, discontinuity in two-phase region when two waters coexist in equilibrium. Actually, metastable equilibrium. Please, next. Okay. And now, this is the last topic of my talk. There is an intriguing possibility, which I'm thinking is very actually provocative and controversial and still questionable. Is it possible to еще не все еще. Я просто прошу внимания. Есть возможность. If there is a possibility to discover liquid-liquid transition in pure water, if we add a solid, and maybe if we find a proper solid which could pull the phase transition line and the critical point to experimentally accessible range of temperature and pressures, maybe we could directly observe the phase transition in this aqueous solution. And this phase transition would originate from the liquid-liquid transition in pure water. In particular, there is a hope because many experiments show that if you have a solute like salts or organic solutes, the line of homogeneous ice formation shifts to low temperature, and probably we could access more close neighborhood of the phase transition. Next slide, please. There is some evidence from, again, from Mishina, from lithium chloride, that could be the same story for the solution, 5% of lithium chloride, with the same story with the possibility of liquid-liquid phase transition in aqueous solutions of salt. Next slide, please. We used the same approach, which was available and commonly used for liquid wafer critical phenomena and supercritical fluids for vapor-liquid transition in water. For this case, the lines emanate from the critical point of pure substance, and they have all possibility. They go to the right, to the left, up, down. Their behavior and all anomalies will change, but everything is controlled by thermodynamics. And because everything is controlled by thermodynamics, the question is what parameter controls this change. The parameter is known as the Krzyzewski parameter under the name of Isaac Krzyzewski, who was a famous physical chemist in Moscow when I was a student, and there was a postdoc at that time. And this parameter actually the difference between two slopes, between the continuation of the phase vapor liquid line, known as the Vidal line, and the slope of the critical line. Basically, if this difference multiplied by the derivative of critical temperature with respect to concentration, we have a parameter which shows either this substance, this solution will behave like pure water, or the properties will change. Next slide. In particular, we applied this thermodynamics for solutions of sodium chloride in water. This is the pure water. Red line, our predicted liquid-liquid transition. Dash line is the Vidal line, continuation of the transition. And the red line, almost vertical, is our predicted line of critical points in solutions upon change in the concentration of salt. So it is 2% of salt terminated of line of liquid-liquid transition terminated at critical point, 5% of salt, 7.7, and so on and so on. Next slide, please. We compared our prediction with only available simulations of salt solutions in water. It is available for so-called TIP4P model, another popular model, but not as well studied as ST2 model. Nevertheless, this model also exhibits the critical point, and if you compare the behavior of this model, which is green, and behavior of real water as we believe, we saw blue and red, we could conclude that quantitatively, at least, our case indeed at least does not contradict to the behavior of the only available model. Next slide. The only experiments for salt water in superfluid region are actually beautiful experiments by Archer and Carter from the United States National Institute of Standards and Technology, just 30 minutes driving from my university to their place. They studied heat capacity and concentration in pure water, which described very well by two-state thermodynamics, and they found the heat capacity dramatically suppressed in solutions. Disappeared completely after few percent of salt, no anomaly. They concluded there is evidence against liquid-liquid transition in supercooled water. I question, does thermodynamics support this claim? The answer, no, it does not. This is exactly behavior which should be in solution, because in solution, the heat capacity anomaly at constant concentration must be suppressed, because it is not isomorphic problem. If they measure heat capacity at constant chemical potential, they would reproduce something. Okay, next slide. So basically, it is a couple of slides and I'm finishing. The heat capacity in solutions is described by so-called crossover formula. It's a background of the heat capacity. There's a strong susceptibility, or you can say heat capacity in pure water. This is the Krzyzewski parameter and concentration. That's all. When we are far away from the critical point, susceptibility is small, or concentration is small, or Krzyzewski parameter accidentally very small. The heat capacity in solutions will behave the same, similar to pure water. If they are very close to the critical point, Krzyzewski parameter is high, or concentration is very high, we can neglect this one, and we immediately have the heat capacity tends to be constant, as small as the concentration and Krzyzewski parameter. Next slide. And we described this data beautifully with two-stage thermodynamics, thus supporting, at least I'm not saying we prove, but we support the idea that in salt solutions there is a line of critical points emanating from the critical point of pure water, and all properties behaves accordingly depending on the concentration and on the rate of temperature. I skip this slide and go to conclusion. And my conclusion is straightforward. Number one, that all available properties of metastable supercooled water can be described with the two-state equation of state, two-structure equation of state, and thus supporting the possibility of the existence of phase transition into liquid structures. Secondly, application of two-state thermodynamics show that in real water, most likely, this transition very much entropy-driven, mainly, while in certain models of water, like ST2, the same phase transition mostly energy-driven. But this is detail. Nevertheless, it's an essential detail because physics is different. What force driving phase transition? Energetically, they are uncomfortable to structures be together, or entropically they are comfortable to be together. ST2 model of water definitely demonstrate the existence of metastable liquid transition at the critical point and beautifully described by our thermodynamics. Peculiar behavior of supercooled aqueous solutions may be indication, maybe, I must be very careful in wording, may be an indication of metastable water's polymorphism, because the solution could be ideal. There is no reason to phase separate the solution of sodium chloride unless this phase transition emanates, originates from the liquid transition. And finally, it's a more specific statement, and I have no idea to go further, but people who deal with thermodynamics of phase transitions, critical phenomena, know that near the critical point of vapor-liquid transition, the other parameter is density. And this is a density is conserved order parameter, like concentration, like number of particles. So it is controlled by diffusive relaxation and diffusive dynamic. It belongs to the diffusion dynamic universality. In this case, in liquid water, structure plays the most important role. The liquid transition in the aqueous system is accompanied by coupling between non-conserved order parameter. The extent of reaction is non-conserved. If I have excess of extent of reaction at this point, it doesn't mean that I have depletion or have less extent of reaction nearby. It is like orientation of water parameter, like a liquid crystal. It is not diffusion relaxation. It belongs to another dynamic universality class. But it is coupled, this parameter is coupled with conserved properties, density, concentration, and energy, and it changes dynamic dramatically. It makes dynamic modern thermodynamics physics and modern thermodynamics. Very exciting, very important, still undeveloped field of this stuff. Thank you so much for your attention.
Thank you very much. We have time for several questions during approximately 3 minutes. The lecture is open to discussion. Please, your questions. Are there any? Yes. Professor Hans, your model.
If you have a critical demixing point, you have to observe some critical correlation of the fluctuations. And there arises the question, why do these critical correlations don't give rise for overcoming the activation threshold for this metastability at all?
If I understand the question correctly, the question, do we have increase of the correlation length?
You have the increasing of correlations of the fluctuations in a metastable state.
Exactly.
That means you have large correlation, large fluctuations, and how can it happen that in this way the activation threshold for the metastability is not overcome?
This is an important question. It's a metastable liquid, and everything depends on the relation or competition between types, which is faster. And I hope that Lars Peterson will talk about it, because there is experimental evidence that the correlation length grow up, and which I hope would support the sigma here. Let him explain about correlation length. Thermodynamically, it should be the same or similar to normal phase transitions. Only in dynamics, because of very tricky coupling between conserved and non-conserved properties, between structural or viscoelastic maybe relaxation and relaxation of the order parameter and density and concentration, dynamics could be very complicated. But thermodynamically, I believe there is no principal objections against normal thermodynamic near-critical behavior near this structure.
Maybe one additional question.
Thank you. It is really exciting to see that a single model can experience so many anomalies for low temperatures. But I must speculate that perhaps some two-stage model exists which could explain some anomalies of water properties for high temperatures, such as compressibility analysis or something like that. How do you think?
This is a chemical reaction controlled between two structures, controlled by pressure and temperature. The density maximum exists at 4 degrees. It means when we go beyond this density maximum, the fraction of low density structure gradually disappears. So about room temperature, the compressibility will go through the minimum. Forget about this. You enter another world of a different world. So actually everything stops, not at 4 degrees Celsius, but at room temperature. Remarkably, room temperature is a border between anomalous low temperature water and more normal water.
Thank you very much. I would like to say that 2 next lectures will be connected with the first lecture, and you may ask a question. If you insist, please ask your question, but very short.
Yes. Professor Nizar, may I ask you, is there some information about the supercooled state of some kinds of heavy water, for instance, for deuterium oxide?
Thank you for your question. I simply have no time. We did exactly the same analysis for thermodynamics of heavy water. Heavy water, a little bit less experimental data available, but they're extremely similar. And they explained and described by the same equations with the same quality. If you, I actually want to ask people who do simulations to study a mixture of heavy water and ordinary water, because it will be a critical line between two waters. It will be straight line, very simple, short, but theoretically much easier to study. But you're absolutely right. Heavy water is but shifted, everything is shifted, of course. By a few degrees.
Thanks a lot once again. I'd like to, before announcing next speaker, the next lecture, I would like to give you such information on behalf of the organizing committee. The organizing committee invites all of us, all of you, to take part in a common photo after the second lecture, approximately in 45 minutes, at the entrance to the building. Please recall it and let us do it. It will take about 5 or 7 minutes. And now I have a great pleasure to announce the next speaker, Professor Xu Limei, from the International Center of Quantum Materials of the Peking University, China. The topic of the lecture is supercritical phenomenon in systems with liquid-liquid phase transition.
So thanks for the chair. First of all, I have to thank to the organizer to have this really nice conference. It's a really great pleasure to be here. This is my first time to be in Ukraine, so I hope I definitely enjoy this conference and also my journey to here. So my talk actually is pretty much related to my health. And today basically I will share my study on this liquid-liquid phase transition based on the analysis for the supercritical phenomena. Thank you. So this is where I'm working now. It's called International Center for Quantum Materials at Peking University. So why we are interested in this liquid-liquid phase transition? So if you look at the literature, you will find that there was a large number of materials that have a really interesting property. So they share many different anomalies. For instance, if you look at the melting line, so they have this negative slope melting curve, and also there was kind of extremely the melting lines. And also some of them have this density anomaly and many other kind of anomalies. So for these kind of materials, if I list just some of them, you can see there was the molecular-like system, for instance, water, nitrogen, and also phosphorus. There are some other materials like the semiconductor materials, silicon and germanium, and some of them even is really highly condensed phase and with strong quantum effect, such as hydrogen. And also we have, the transition metals like cerium also share some kind of features with these anomalies. So all of these materials, if you look at them, they're pretty much, very, very much different because we have really different chemistry. So we have this molecular system, a semiconductor, and also some of them can be conductor. So the question that we are interested in, these features, or are these features, they're related, or if they're related, if they're relevant to this liquid-liquid phase transition, and if so, how we can determine this liquid-liquid phase transition, and also the critical point. So in my case, I will just use an example, especially to the study for water, because these the materials that we have the most number of data. So I will use this water as an example to look at, how these anomalies relate to this liquid-liquid transition and how we can determine the critical point out of that. So here's the outline of my talk. So I will briefly mention, the experimental data and have a brief review about the general data that the experiment have, and then propose the question that we are going to ask. And once we propose the model, we'll give you how we can understand these water-like anomalies using the supercritical phenomenon behavior. And finally, because many of this data is related to this liquid-liquid phase transition, and also started in confinement geometries. So therefore, I will give a brief study about the confinement effect, and also the surface of chemistry on the liquid-liquid phase transit. And finally, give a brief summary. So why are we interested in water? So there are many kind of reasons that we are interested in water. So here I just list two of them. So the first one, you can see that everybody knows that water is a really important solvent. So it's really important for the study of chemical reactions and also to understand the normal function of biomolecules. So here it's just two illustrations. For instance, in different states of water, you will see that the materials or the slope looks different. So if you can just look by eye. So here the left side is the high density water, and the right side is the low density water. So the polymer, if you put into the water in the two different states, for instance, you can control temperature or you can control the pressure. So you will see that the polymer have a quite different behavior. So in the high density, you can see that the polymer is really like water. Have this chain polymer, but if you put the polymer into the low density water, because we know that the low density water prefer to form tetrahedral structure. So therefore, water does not like polymer. So in this case, the polymer forms a kind of a denatured state to include the volume, the surface water with this water. So the second reason that we're interested is because the water basically have these anomalies that is kind of a prototype for other materials, especially if we compare with the group 4 materials in the chemical table, periodic table. You can see that water can be placed somewhere between copper and silica. So the understanding of this anomalous behavior for water, basically we can give some indication for the understanding of other materials sharing the same anomalous behavior. So so what are the anomalies? So if people really in the field of water, you probably know that there are more than 63 water anomalies that either found by experiment or by computer simulations. There are many of them. So here just list 3 of them. Probably you can quite familiar with them. The first one, of course, is kind of density anomaly. So this was known for more than 400 years ago, but why water has such kind of anomaly, nobody really knows. Even though we have some hypotheses, but we still need to confirm whether or not it's true. So you can see that for simple liquid, it's just as you're going down to lower temperature, so the liquid becomes heavier and heavier. So that's about, for water, you can see at ambient conditions, so there was a 4 Celsius maximum in the ambient conditions. So this is very different from the simple liquid. So that's also why you can see that the solid ice is floating on top of liquid water. So there are some kind of anomalies that you probably also can heard about that. It's the thermodynamic anomalies. For instance, if you look at the thermodynamic property, for instance, like the specific heat and also the isothermal compressibility. For each of these 2 properties, you can see they can relate to thermal fluctuations. For instance, for specific heat, it's a thermal fluctuation related to the entropy, right? And we know that as you go down to lower and lower temperature, the thermal fluctuation should going down. But you can see compared to water, this is quite opposite. At a temperature higher than 35 Celsius in ambient conditions, so it's normal liquid. It's going down as you lower and down to low temperature. However, once it crosses to this temperature, it start to increase sharply. And similar behavior for compressibility. It's also like, of course, this minimum has at a different temperature. But you can see the behavior. For the simple liquid, it's monotonically going down as you're going down to lower temperature. So this is consistent with the thermodynamic relations. But for water, it's opposite. Actually, as you're going down to even lower temperatures, this anomalous behavior becomes more distinct. So this is the experimental data back to 1970s. It's from done by Austin Angel and by Spady. So you can see that as you're going down to the lowest temperature, the non-confined water can access. So it's basically roughly around 240 Kelvin. So this is the lowest data that one can access. If you try to fit in this data near the lowest temperature that you can access, you'll find some kind of parallel scaling behavior. So with the feeding temperature, roughly about 228 Kelvin. So the question now is, we know that near critical point, you can have this thermal, diverging. It's like a diverging behavior here. So does this mean that there is some kind of a critical phenomenon here? So we don't know yet. So later on, before we go to why this happens, so maybe we take a minute to look at the phase diagram of water. For instance, we know that this is for ambient condition. So just at 1 atmosphere, you can see this stable water between 0 and 100 Celsius. It can also have this stable liquid. Metastable liquid. It's called superheated liquid above 100 Celsius. And if you're going down to lower temperature below 0, we know that it's supposed to become ice. But if you're cooling the system rather slowly, and your surface is clean enough, and then you can get this super cool water. So this super cool water can stay in the liquid phase even down to 240 Kelvin. So that's the lower limit the experiment can attack. So below that, so the destination for the liquid is to become ice. So people call this no man's land. And I think it's back to 1980 something, as Mishima found. He did another experiment. So instead of cooling really slowly, what he did is he quenched the liquid really fast from the high temperature side. So in that case, you can cool it down to much, much lower temperature, for instance, 170 Kelvin. And in this case, we didn't get, the ice, but it get amorphous structure. It's called glassy water. And if you melting this glassy water up, you're heating up, so there was two destinations. So you can see that there was a regime, so this glass can become ice. Of course, if you're heating too fast, it will become a liquid. So this basically, the experimental data that one has for water. And later on that, for this glassy water, it's quite new, because we don't know that before. And then you can see that if you pressurize, so this ice water down to really high pressure, from 1 bar to 0.5 gigapascal, for instance, you can see that this amorphous water going through a first order phase transition. So what it is, you can see that you compressorize, so there was a really sharp transition in terms of volume. So this is just illustration for the low density amorphous, so the local structure look like ice. And there's another one, it's called high density amorphous. The structure is not similar to tetrahedral structure. So later on in 1992, Peter Paul did some computer simulations. He found something really nice. So in this no man's land, he found some liquid transition, and this line is hypothesized to be the continuous transition from the low density amorphous to the high temperature and the low pressure side, and then terminate at critical point is called the liquid critical point. So people hypothesize that it's maybe because of the existence of this liquid critical point that water have all kind of anomalies. So after that, there was a lot of people, from experiment, from theoretical, from computation. So they want to look at, if this critical point exists or not. So the question is, so this critical point basically located in a no man's land region. So it's below the melting line. It's deeper. It's kind of deep below the melting line. So that's why it's really difficult to attack in terms of liquid phase. So therefore, even though people tried a lot, but still, it's not extremely clear yet. So the experiment is some kind of solutions. What they do is they confine the liquid into a nanostructure. So we know that the lower limit that you can access liquid water is 240 Kelvin in ambient conditions. But if you confine water, for instance, in these nanogeometries, what you can access is a much lower temperature. It still can remain liquid. For instance, you can down to 200 kelvins, can still be the liquid phase. This is because these nanogeometries, the confinement effects, stabilize the liquid phase and also kind of avoid crystallization in such kind of system. So let's see what experiment get by confining water in these nanogeometries. So this is the data that people already have back to the 1970s. You can see that this specific heat is increased really sharply around this 240 Kelvin, or looks like there was a turning point at 227. But if you confine water in this nanogeometry, you found that it's not diverging, but instead there was a crossover, so there was a maximum near this point. And later on, more or less similar times, so people already also look at the dynamic property for the system. So what they found is, more or less near similar temperatures, so they found a dynamic crossover. So the point is, whether or not this is related, and if this is linked to the critical point. So here's the question that we are going to ask. Instead, we use because the experiment can only have a limited number of data. Then what we can do, we can use computer simulations, try to answer the following questions. What happened? Okay, the first question is we're going to answer, try to interpret what happened to the experiment data. So if we look at the data before, it looked like a divergent effect. And then now we confine water into nanogeometries. We saw something is not converging, but diverging, but it's a maximum over here. So we want to look at, why this happens. And second question we want to ask is if this is related to the hypothesized liquid critical point, and if so, and then how we can detect the critical point. So what we want to do is, so here's the deal. So we want to construct a model that basically have two features. So the first one is have to have accessible liquid critical point, because we know that in experiment you cannot. But we can take advantage for the computer simulations. We can build something that have this liquid critical point, and if we have this critical point, then we can look around what really happens near the critical point. So if we get something that is similar to the experiment data, so we can map each other. So therefore we can detect whether or not the critical point exists or not. So for instance, in terms of water, so we can use, because we list several materials at the very beginning of the presentation. So it's not only water, they have a group of materials that shows the liquid, indication of the liquid transition. So therefore we try to, take out as much information of water as possible. So we just use a cost-grading models. So for instance, the water, we know that it's 1 oxygen, 2 hydrogens with some angles between them. So instead of using this molecular structure, we use some cross-grain particles to take place in the water molecule. So therefore, we have this one sphere, another sphere, so they interacting with each other through potentials that we're showing right here. So for instance, we know that if you measure the structure information from the liquid water, so here's what you get. So here's the interaction energy between these water molecules at ambient conditions, room temperature. So the gray one. So this is the gray one. So this pink is for the interaction between hydrogen bonds. Because I told you that I not only care about water, but I also care something else. For instance, silicon and germanium, they definitely do not have this hydrogen bond. So therefore, I use something much simpler to simplify this interaction potential by two runs. One is the hardcore interaction, so basically you can mimic the strong repulsion when the two particles are moving close to each other. And then you have this kind of a weak interaction between two particles. When they are at a certain distance, you can stabilize the liquid into one of this minimum. So basically the key feature is, first of all, is the coarse grain. A second, have a spherical symmetric. And the third one is have a 2-length scale. So this turns out to be extremely important in our study. So this is the first length scale, and this is the second length scale. So why we think this one possibly have liquid critical point? So if you look at this, the potential that we're going to use, it really looks similar to Lennard-Jones potential. So we know that Lennard-Jones potential basically does not have a liquid-liquid. So the reason is, so this one only have for one minimum, so which means you only have a one length scale. So in this case, you only stabilize one liquid phase. But for this potential, because we have two length scales, for instance, if we look at the phase transitions, we can look at the Gibbs energy for the system. Basically, it's the internal energy plus PV minus TS, the entropy term. So if we just use the simplest case, for instance, temperature equals 0, you can see that this is really similar to all potentials because we have two length scales. You can have one here and the other one here. As you changing the pressure, you can gradually switch the stability of these two states. For instance, the low pressures, the low density liquid is stabilized. But if you gradually increase pressure, you can say at some point, these two liquid phases can be equally coexist. And the high pressures, of course, we can stabilize the high density liquid. So therefore, you can see that we have some indication. We are not starting from nothing. So we have some roughly estimation what we can get. So we just run really simple computer simulations, molecular dynamics simulation. You can see that clearly. You can see they coexist for two liquid states. So there's a high density and there's a low density. And if you look at the structure of them, so this is the first shell and the second shell. So they different by a lot. So for the high density liquid, there are more number of particles, pushing up to the particle, while in the low density liquid, more particles are sitting in the attractive well. So, and if we, if we look back about, think about water. So there was another property for water to have this amorphous structure. So low density amorphous and high density amorphous. And in this model, you can see if you quenching the liquid from high temperatures, we also can end up with the two amorphous state. So this is the low density glass, and then this is the high density glass, and they also different by structurally different. So in this case, at least we can show in this model it's very simple, but you can see this shows the water kind of properties for this glass transition. So this is, for instance, if you compress the low density glass, compressorize, you can see that it goes through a first order phase transition. It can be really sharp transition at some point. So this is the final ending point. So you start from this low density amorphous, and then you pressurize in, and you can end up with a really high density amorphous. And these two transitions is kind of a first order phase transition. So if I summarize, I didn't show all of them. I summarize, can try to convince you that this model is simple enough, but it definitely shows the key features that we try to looking at. So first of all, remember that we want to get a model that with a stable liquid-liquid crater point. So here it is. So this is the stable liquid-liquid crater point, and this is the melting line. Is just above the melting line. So that's why it's stable. Therefore, we can look around what really happens near the crater point and then compare with the experiment. And for this melting line, you can see that we have this is a negative slope. So this is pretty much similar to what is observed in many metal systems. And also we have this kind of a melting extreme along this line. So there was a kink over here. So you have these features. And also we have other water kind of anomalies, such as density maximum. So this is in the PT phase diagram. I just put all of the data right here. So this is the density maximum region. And we also have this density minimum region that was later on observed by experiment. So you can see this is the density anomaly region. And we have this low density liquid, high density liquid, and low density amorphous, high density amorphous. So now we have all of this model, and the model have all the features that we want, and then now we can do experiment, what really happens near the crater point. So we will do, first of all, we will do 4 experiments, computer experiment. So first we do one quench, gradually decreasing temperature along constant pressure below the crater point. And we also do another 3 experiments above the crater point. So let's see what happens. So if we first measure the specific heat of the system, you can see that, this below the critical point. You can see this coexist line. So we probably imagine that because coexist line is the first order phase transition, you're supposed to see something like a discontinuity here, but unfortunately it's not. And also above the critical point, so we know that all of the difference between two phases disappear near the critical point. So in the one phase region, we probably don't expect to see anything. But you can see what we see is something really interesting. So first of all, there's a peak as you're cooling down, in the one phase region. And secondly, so this peak, as you're moving closer and closer to the critical point, so this peak becomes sharper and sharper, okay? And also the position moves, and in the end, it's end up with the critical point. So if we locate all of this maximum to the phase diagram, so we name it called William line. So this is the response function maximum. Okay, so this means that in the one phase region, according to what we learned from statistical physics, is not supposed to see anything, but we now found some response function maximum, and really can be measured by experiment. Actually, it's not only for this specific heat. There are many other thermodynamic quantities, such as the isotherm compressibility, also shows similar behavior. And then, because experiment also mirror the dynamic properties, so I also show you 3 experiments in the computer experiment. First of all, we do one, cooling in the low density liquid, and then we do one heating in the high density liquid. So the third one is we do cooling in the one phase region. Let's look at how these dynamic properties behave. So this orange line is basically for the low density liquid. You can see that this diffuse coefficient gradually decrease as you're going down to lower temperature. And for this low density liquid. And then if you look at the high density phase, this is really different from the low density. The dynamic is really different, right? You can see in the high density phase, the diffuse coefficient is lower compared to the low density phase. They separate. But if you look at this one phase region, what do you expect? So we see that, as at high temperatures, so this line, the green one, basically follows the behavior of low density liquid. And at the low temperatures, it follows the behavior of high density liquid. So there was a kink between these two. And this kink, the temperature where these two behaviors departures, is more or less near the William line temperature. Okay? So now we can see that we can tell experiment what exactly you can do to detect the critical point. Okay? You can either looking at the response function maximum, or you can look at this dynamic property crossovers in your system. And then not only that, you can also see the structures show similar behavior. So we have 2 ways to define structure. First, we can look at the translational order in the system. For instance, if you're periodical in lattice structure, you get really nice, you can get some behavior okay. So this first one, this is the orientational order parameter. You can see we can define this orientational order parameter by this harmonic function. So this is the spherical coordinate, theta and phi. So you can look at how it's locally packing near center atoms. So if you, for instance, we do 3 experiments, 1 below and 3 above. So this is really similar to what we see in thermodynamic properties. You can see that as you moving closer and closer to the critical point from the supercritical region. So basically, we call this the supercritical region. And you can see this, first of all, there was a maximum, and second, this maximum becomes shorter and shorter as you move closer and closer to the critical point. So therefore, you can also trace the critical point, so the ending point. So for instance, if you move further, along some line that's really close to the critical point, you should see the structure behavior is divergent. So therefore, you can trace the critical point also by the structure behavior. Okay? And finally, we will give you another example about the response function. It's called the translational order. So before I show you, how this system is locally oriented, and this is a long-range order. If there's a long-range order, so you can get this parameter, really different from other one. You can see that as you decreasing the pressure, so this is really far away above the critical point, and this is in the middle, and this is quite close to the critical point. You can see the translational order also shows some indication. So there was some change in the one phase region, and to see clearly, so this is the derivative for the translational order. Similar to the orientation order, you can see that as you're moving closer and closer to the critical point, so this response function becomes sharper and sharper. And until the end, if you're extremely close to the critical point, so this becomes divergent. So therefore, you can see the structure, dynamics, and also thermodynamics. All of the things give you the indication that you can use them to trace the critical point in your system. Now let's compare with all results with experiment. So this is what experiment had before for the nanopore. You can see for specific, there is a maximum over here because there is only one line that an experiment can get. We have no idea which part of the phase diagram they are. And then if we compare to the simulation in all data, because we can search everywhere in all phase diagram, therefore we know what exactly happens in each part of the phase diagram. You can see in the one phase region, actually we didn't see this response function maximum. So therefore this is definitely not corresponding to the two-state phase. However, in the supercritical region, you can see that we have this specific heat maximum. So this is pretty much similar to what experiment observed. So therefore we can say that what experiment detect here is more or less for instance, this is a long ending condition. So this is actually in the supercritical region of liquid-liquid water, if there is a liquid-liquid phase transition. Similarly, for this self-diffusion, you can see there was a kink over here. So as you changing pressures, so the crossover temperature for this kink also moves. And until if you go to one phase region, there is no kink. So therefore, you can by seeing if there is a kink or no, so you can determine where is the critical point, similar to what we have here. So you can see that by compare the computer simulations with experimental results, it shows a lot of similarity of this data corresponding to the supercritical region of the liquid-liquid water. So here's the the real phase diagram that get from experiment. So before, if you want to look at liquid critical point, it's basically in this region, this really bad region. Why? This is really difficult, really easy to crystallize, and so difficult to access in liquid phase. So therefore, it's not a good idea. So according to our study, so instead of looking here, we can look at something that's much easier. For instance, high pressure, lower pressure, and high temperature. For instance, this region, for instance, you can perform cooling study, and then look at if there is this response function maximum. So you can perform many of these studies. For instance, you can perform another constant pressure studies and look at by tracing this maximum. So basically, you can tracing all of these points. So this is basically the response function maximum for this one. And the terminal point, so basically is the liquid-liquid critical point. So of course, as I said, not only thermodynamics, you can also use thermodynamics and the structure information to detect this critical point in the system. So by now it looks really nice. It means that the theoretical study, the experimental observation is kind of a support the existence of a liquid-liquid critical point. But there is so this is the first experimental study that basically using all theoretical predictions. This is performed by Professor Shou-Sing Chen from MIT. So they basically found something that really similar to what we observed. Okay, so if I give a really brief summary for the first part, is for instance, this is the real phase diagram that one should know. So before we only know the coexistent line and the critical point are really important. But actually, in the supercritical region, there's something that is really, really measurable and also can be used to do something. And so basically, we call this Witten line. So this Witten line, basically, you can be applied to many different materials to detect the second critical point, even in this highly condensed phase. So in the end, if I have time, I will show another example. Okay, so by now it seems to be, pretty happy. So we have, we have quite consistent pictures about the liquid-liquid transition in water. But there is one thing that I have to remind you that, this is the data from the bulk data. There was no kind of constraint for that. However, this data is from the confined water. So the question is, if this data, if you can map directly the data from confined, nano geometries directly to the non-confined water. Okay, so this is a really serious question, because if yes, means the liquid krypton, it is there, and if not, then we have big trouble because we don't know what this data means. Okay, so if we look at these two systems, so basically they're different by additional dimensions. For the bulk case, we know that the properties of bulk water can be controlled by temperature and also pressures. But in the nano geometries, there was additional dimension. So it's depending on the way that you confine your system. For instance, if you are sandwiching confine your system, so additional dimension is the separation between these two surfaces. So you have one dimension, additional dimension, the separation between these plates. And if you use confinement, finite size confined surfaces. In this case, you can see you have additional dimension. The size of the surface also play a role. And additionally, so we know that if you confine liquid with different surfaces, the interaction that looks different. If not for all of the liquid, but at least near the surface, it will look different. So later on, in the next section, we'll talk about how does this additional parameters that can affect the behavior of the phase transition, and therefore we can justify if the experimental data is good or not good, or if not, and then which range is good to use. So here's just to give you a brief idea that how we can characterize the surface chemistry of this system. So in all studies, basically we use a parameter called the contact angle, and this contact angle basically is the characterize the interaction between the liquid and the surfaces. For instance, you can turn on some interaction parameters. Here we call this the interaction strength. And if this interaction strength is really small, so means the system is extremely hydrophobic. So you can see the contact angle. And if you, so the contact angle is more than 150. And if this interaction strength is extremely high, so this means, the liquid is just prefer to stay on top of this interface. So therefore, this is extremely hydrophilic. And in the middle is just, between hydrophobic and hydrophilic. So the contact angle basically determined by the profile of this droplet. So you can just make a many, ensemble average and to get a really good estimate for this surface chemistry. Okay, so we study a couple of properties for that. So the first one is we want, we check the surface chemistry. How does this one will affect the density anomaly? So here's how we determine the density anomaly. For instance, for each of these, constant pressures, you can plot the density of the system as a function of the temperature. You can see there's a maximum along each of these pressures. So you can map each of these pressure on this PT phase diagram. So this gives you the density anomaly region. This is the high density, this is the density maximum. You can see that for strongly hydrophobic, so this density anomaly is shrink. First of all, the region is shrink, and the secondly is moved to the low temperature side. But for the intermediate, this is about contact angle 90, and this contact angle roughly about 0. So this is extremely hydrophilic. So you can see that for these two cases, the density, at least the density anomaly doesn't change much. So this means hydrophobic. So if the confinement surface is hydrophobic, then this is really dangerous. Okay, and then here's the critical point that we determined by the end of the Widom line that I mentioned to you. We can determine by actually here, this one is determined by the compressibility maximum. So you can see that, for different way of confinement, for instance, if you it's extremely confined. 5 or 8. It's just less than 5 layers of liquid in between these two plates. You can see the critical point. Just look at the critical pressure. So this is really far off. Okay, so this is a really high pressure, and then of course this for the bulk case. As you separating these two plates further and further away, so in the end the critical point should converge to the non-confined case. So there was you can see that it's more or less around 15. So this is the normalized parameter. So 15 is roughly about 7 to 8 layers of liquid in between. Okay, so in this case, so lower than 15, so the confined data does not overtop. You cannot leave top of this data on the bulk liquid. Okay. But after that, it's more or less okay, at least in terms of this critical point, the critical pressure. We also check, the interplay between confinement and the surface chemistry. You can see that, first of all, you can look at for the highly confined and lessly confined. So they are plotted in the same scale. So for highly confined, of course, it's shifting to high pressure. Okay, and for different surface chemistry, so this is really confined. This is a super hydrophobic, and this is hydrophilic. You can see that hydrophobic is moves to lower temperature and high pressure. So they both play a lot of roles. Okay, so this means the confinement data is not straightforward. You cannot apply directly to on top of this bulk data. So here's the summary for the second part. So for instance, according to the study for this confinement, the surface chemistry and also the confinement dimensions, we know that the phase behavior definitely depends on the confinement. And for hydrophobic confinement, the liquid-liquid transition actually is quite different from the bulk data. And for the hydrophilic confinement, so if the if the confinement is not so severe, for instance, the number of liquid, the layer of liquid in the confined geometry is more than 8, and then probably you are safe. But less than that, the system just changes dramatically. It doesn't look like the bulk liquid. So if we go back to the experimental data, so we love this circle, so that was the bulk data, so this is the confinement data. So this have a requirement. So if you want to apply your, your confinement data on top of this bulk data, so it requires your dimension. For instance, if you were in the nanopore, has to be more than 8 layers, at least according to all studies. Okay, so this put a lot of constraint to the interpretation of the experimental data. Okay, I give so I probably will stop here and give a really brief summary for all of that. So first of all, we basically want to understand the liquid-liquid transition, but it's based on the supercritical phenomenon in the liquid phase. We construct a very simple model. This model has all water kind of anomalies. And not only that, it also shows, we take out the hydrogen bond behaviors. So therefore, this is quite a general model. And this model has a very stable liquid-liquid bond, which is really important for the study of this critical phenomenon. So therefore, we can explore everywhere in the phase diagram and can compare with experiment. And the second one, we according to all study, because this model is not water, so we cannot call it water because there was no hydrogen inside. And also there are some other difference I didn't tell you exactly, but it shows all water kind of anomalies. So this means, the water kind of anomalies may not be due to the hydrogen bond, okay? And may also not due to the tetrahedral liquid, because we know from experiment that water, silicon, germanium, so they all share similar anomalous behavior. And the other thing they're similar is their structure. This stable structure is tetrahedral structure. But according to all studies, because all model, the stable structure is HCC structure. So therefore, it also may not be due to this tetrahedral structure for this anomalous behavior. But there was a key message here, is all of this anomalous behavior may be because the existence of two-length scale. This may be kind of ambitious, but I think that's the conclusion that basically we can get from our model study. So it's due to the two length scales exist in the system. And also we propose the concept of the width line, and then we can use this width as in the supercritical regime, and we can use these width lines by tracing the width line, ending point, basically giving you the critical point. So you can use this one to detect the critical point. Actually, it's quite successful in the study of liquid water for experiment. And finally, I will not show you the details, but just give you a finalized structure pictures. So actually, the concept of the width line or the supercritical phenomena is we first observed in this classical system. Actually, it can also be applied to really condensed system, because we know hydrogen is the smallest atom that we know, and they have a strong quantum effect in that. And we basically studied this what happens to the liquid-liquid phase transition in hydrogen using this quantum dynamics. And we found exactly similar behavior as what we see in the classical system. So you can see that this is the conductivity of the system. So as you move closer and closer to the critical point, the conductivity becomes sharper and sharper. It's a continuous because there's a maximum here. And also the response function becomes, there is a maximum over here. And secondly, you can also look at the fraction of the hydrogen atoms and also the fraction of hydrogen molecules, because the hydrogen atom is the contribute to the conductivity, while molecules can be insulating system. You can see that this structure also gives you the information that the exist of this width line here. So by tracing the ending point for all of these response functions, basically we can also detect the liquid critical point in hydrogen, because we know that from experiment, so the exist of this the critical point is at really high pressure, and then this many kind of more than 100 gigapascal is too difficult for experiment to go to that regime. So therefore, what we propose, instead of looking at this really difficult regime, so you can look at something at higher pressure and lower pressure and high temperature side. It's much easier. So therefore, you can treat the critical point. Okay, finally, I will give acknowledgement to my collaborators and also to acknowledge the support from these three resources. Thank you for your attention.
Thank you very much. Let's open to a very short discussion. Question.
So this is a very good question, because I don't know about experiment, in all systems we know clearly, which part is the low density light, which part is the high density light. So for instance, if you look at, not sure if I can. Yeah. So yeah, you can see that this data that we get. So this is for the this is purely low density phase. This is in the 2-state phase, and then you can see there was no crossover, right? But if you look at this green one, it's basically in the supercritical region. So clearly there was a kind of a kink over here, and you can see the data is a departure from this low density liquid at some point. So I don't think it's it's a need to be clarified, because the data tells everything. Okay, this is a really good question. I think the structure makes a lot of difference. So if you remember the structure of the system, for instance, the orientational structure and also the translational structures, it has some behavior at one side, a high temperature side, and also shows another behavior in the low temperature side. So I believe that is due to the structure, because you can form kind of a local packing, and this local packing definitely will affect the dynamic properties of the system. Yeah.
I ask a short question. You mentioned about dependence, your results on so-called low crossover dimensionality. which means that you have different shape of confinement, so say cylindrical core and slit-like core. For cylindrical, you will have larger shift. Did you receive experimental results or contour simulation results for this concept?
So we compare with the experimental data is for the nanotube. It's one-dimensional nanotube, and all data actually is 2D confined. We just confined within the sandwich. Yeah. But I believe that they should share the similar features. We probably will move, we probably will do another test for this nanopore confinement. Yeah. But of course, we didn't see too much, strange confinement because that definitely will affect the fish behavior.
And what maximum shift of temperature phase contribution did you receive?
Can you repeat?
What is the value of temperature shifts?
You mean in terms of the real unit? So this is a good question because we use this cost grain model. So I actually didn't compare the real number. I only can tell that it's how many layers of liquid that is safe for you to draw the conclusion for this confinement data. Yeah.
Thank you very much.
Yeah. Thanks.
As I told all of you are invited to go downstairs to the entrance of our building and take common water.
For inviting me here, and it's my first time in Ukraine, and it's very hot. Now, I'm used to actually walk around, and with this stationary microphone, I'm kind of stuck. So if I start to walk away and try to show things, please stop me, okay? Now, what I have here on the screen is a result from a molecular dynamics simulation of water. It's very super cold condition, 253 Kelvin. What we have done is we've characterized molecules as being either very tetrahedral, we use a Q parameter to characterize tetrahedrality. Those we color in blue, those regions. Now, in yellow, we have high-density-like structures. And as we can see here, these two properties are anti-correlated. And when we talk about this, we usually call it Swedish water because that's the colors of the Swedish flag. I guess it could be Ukrainian water as well. Actually, in the European Championships, it was very confusing when Ukraine beat Sweden because both teams should have been blue and yellow, right? So, anyway, what I will talk about now is a combination of experimental theories. The experimental side is headed by Anders Nilsson at Stanford. And we have a large experimental side and then also a theory side. And I should especially mention Yuri Shostebruch, who is from Kiev and is doing his PhD with me in Stockholm, calculating X-ray absorption spectra. Now, you've seen this, so I will only focus on a couple of aspects here. So we have the isothermal compressibility, the heat capacity, the thermal expansivity. What's characteristic of all three here is that they depend on fluctuations in the liquid. So we have volume or density fluctuations determining the isothermal compressibility. We have fluctuations in the entropy determining CP, and the cross correlation between them for the expansivity. Now, we have this divergence, and the crazy thing with water is that fluctuations in the liquid increase, as we call them. And that's a direct indication that these fluctuations have a different origin than thermal. Now, I will give you an outline, sort of, and a roadmap for this talk here in terms of different experiments. Well, first of all, I'm a theoretician, so I do MD simulations, spectrum calculations, and it's Anders Nilsson who does the experiments. But he and I have been working together for almost 20 years, very closely. So it will all be very mixed between experiment and theory. Now, from X-ray absorption spectroscopy, we concluded back in 2004 that most molecules are actually not tetrahedrally coordinated or hydrogen bonded in liquid water, but instead hydrogen side. So we will be very sensitive to dominated hydrogen bonds, but insensitive to what happens on the back of the molecule in accepted hydrogen bonds. It's a very high, it's of the order of 540 electron volts. So it's a highly excited state, which means that it has a short lifetime. Then we get a decay. The dominating channel is, of course, Auger decay. But a minority channel is fluorescence. Then we get an X-ray photon out that can be detected. That gives us a direct measurement of the energy difference between the valence states and the core level. Here's what we see then. So this is gas phase of water. Now, when we remove the 1s electron, we basically make oxygen into fluorine, because we remove one screening charge. For the occupied, the bonding levels, 1b2 and 3a1, there would be large vibrational excitations, because FH2 plus is not happy in the geometry of H2O. So we get Frank Condon broadening and they become smeared out. But the lone pair, the non-bonding lone pair, remains very sharp. And in the liquid, we get two sharp peaks, which I will come back to. So, X-ray absorption. When we did this for Anders, it's a difficult experiment, and Anders was the first one to be able to measure at the oxygen kh of liquid water. We were not interested in water. We wanted to look at biomolecules in water. But in order to see the biomolecules, we had to have a background spectrum of water to subtract. But that background spectrum did not look as it should. And what would one expect from a tetrahedral model of water? Well, it should be similar to ice. Ice is very tetrahedral. Okay? Now, we get a sharp conduction band in ice because the distances are well defined. There are similar distances. And since we excite into unoccupied states, the position of the anti-bonding orbitals depends on the distance between molecules. So if we have more disorder, if water is like ice, tetrahedral but more disordered, we would expect a smeared out light spectrum. Many different distances, many different energy positions. That was not what we saw at all. This is the X-ray absorption spectrum of liquid water. This is the spectrum of ice. So they're very different. So in the liquid, we lose basically the tetrahedral signal that we see in ice. We get a new sharp feature here that we call the pre-edge. And we get this main edge, which becomes very strong. This is ambient temperature, room temperature. But here's a comparison between 4 degrees and 90 degrees. So the differences are small. Now, what we see is what we would expect from this difference. That when we heat the liquid, we lose intensity in this region, which we call the post edge. And that's the region that is strong in ice. And instead, we gain intensity in the pre-edge and the main edge. So intuitively, we would associate the pre-edge and the main edge with breaking hydrogen bonds. Now, what we did was to do a lot of MD simulations of water. We took out different structures and calculated the X-ray absorption spectra. And this is what we find. If we take the structure of ice, we have a good representation. If we look at, from the simulations in the liquid, take out molecules that have 4 hydrogen bonds, we get something that looks like ice. If we break an accepted hydrogen bond on the backside of the molecule, it still looks like ice. But if we break one of the donated hydrogen bonds, making the hydrogen bonding asymmetric, then we lose intensity here, we gain it at the pre-edge, we gain at the main edge. So this is a theoretical prediction. But then Anders could go back to surface science and on a platinum substrate build a film of ice. Ordered, overlaid. Here we have an extreme asymmetric situation. One donated and one hydrogen pointing to vacuum. Looking with the X-rays straight down, you basically only see bulk water, tetrahedrally coordinated. And you get a spectrum like this. Looking grazing along the surface, you mainly see these molecules, and you have a spectrum like this. Very strong pre-edge, almost no post-edge. To make sure that we only look at these and not defects inside the ice, we can put down just a monolayer of ammonia, and that quenches these free OHs, and you get an ice-like spectrum. So we have a good assignment of the pre-edge and the post-edge. Now what about the main edge? Well, the main edge turns out to be very sensitive to the packing or the density in the local density of the molecules. So these are now spectra of different ices. Now going from hexagonal ice with a density of 0.9 grams per cubic centimeter all the way up to ice 8 at 1.6 grams per cubic centimeter. And what we can see is that we have a shift in the ratio between post-edge and main edge, where the main edge grows more and more. This can be correlated to the second shell distance in the pair correlation function. And it's a linear relationship. So here we have the main edge to post-edge ratio. Here we have the second shell distance, and they all line up. Similarly, we can correlate to the density. But then the liquid falls off the curve. And this is an indication that in the case of the liquid, we might actually have a heterogeneity. That the main edge to post edge are determined, that the second shell distance is determined by one component in the liquid. And this would be the low density liquid, which has a very structured pair correlation function, while the high density-like component has a very flat pair correlation function, does not contribute to the second shell. Okay? Here's X-ray emission spectroscopy now. So on the left we have the full spectra. Here we have gas phase. Here we have crystalline ice, and we can see there's a shift between gas phase and the condensed phase. Now, in the liquid, we get a split with one peak close to the gas phase and the other peak close to the position in tetrahedral ice. We have a sequence of different temperatures, and we can see that when we heat the liquid, the peak here, which is close to the tetrahedral position, goes down in intensity, and instead the other one grows in intensity. Here we zoom in to just this region. And what we can see is that this peak that we will call tetrahedral stays at a fixed energy position and decreases in intensity. While the other one increases in intensity when we heat the liquid, and it also shifts towards the gas phase, which means that somehow it gets thermally excited, and the hydrogen bond network becomes more and more weakened and approaching non-hydrogen bonded like gas phase. Okay? We don't see any broadening. There are no new features coming up. So it's just a conversion of intensity from this to that, and a thermal excitation of this component. We can connect the two spectroscopies because X-ray emission comes after the absorption, which means that we can use the photon energy to select where on the liquid spectrum we do the excitation. We need a reference, and the reference will be at 550 eV, where there's no structural sensitivity. The reference is this black line here. We can see if we excite at the post edge here, we excite where we have growing intensity when we cool the liquid, and we get a higher signal of the peak which grows when we cool the liquid. So they are connected. When we excite at the pre-edge, which in the science paper we assign to uniquely asymmetric hydrogen bond situations, we only get one peak. So we can select which type of local structure in the liquid that we want to measure. Just a summary, we assign tetrahedral structures as a minority at ambient conditions, distorted structures with only one donated hydrogen bond, the other basically free, as a dominating contribution at ambient temperatures. We interpret this in terms of a competition between enthalpy and entropy. So this is very much similar to what Professor Anisimov discussed before. And we see this now in the experiment. We convert from this type of structure over to this. This does not get thermally excited. This one gets thermally excited. So we can assume that this new or other component can contribute to the entropy at higher temperatures. We see similar behavior in the pre-edge and main edge in X-ray absorption, that they shift towards the gas phase. The way we interpret this is in terms of the librational excitations in the liquid. Now, if you are tetrahedrally hydrogen bonded, the molecules try to rotate, but they rotate against 4 hydrogen bonds, which makes a very sharp potential, which then, when we quantize, gives large steps. So the steps, the frequency, the libration modes in ice are around 800 wave numbers, which is like 3 to 4 times kT at room temperature. So they will not be thermally accessible. They will not contribute to the entropy. If we break hydrogen bonds, the molecules become freer to rotate. The potential energy surface comes down, becomes flatter, the level spacing comes down, and we can now thermally populate these levels. And there we have a contribution to the entropy. Okay, so small angle X-ray scattering. So this is now done with X-rays. We have very short wavelengths. But by going to very small angles, we trick the light to see correlations even at very long distances. I will assume that you're familiar with small angle neutron scattering or X-ray scattering. Basically what we will see here are density inhomogeneities in the liquid. And we can extract also the length scale of them. On the left here we have a normal liquid, the temperature-dependent small angle X-ray scattering of ethanol, normal alcohol. What we can see is that as we cool the liquid, we just have progressively less and less scattering as the thermal disorder in the liquid becomes less and less. Now, for water, on the other hand, here we go from room temperature, 284 Kelvin, it's a cold room. And as we cool the liquid down to minus 21 degrees C, we see an enhancement of the scattering at low Q transfer. This is connected to the isothermal compressibility. And this has been extracted from sound measurements, sound velocity measurements in a liquid. And that's the dashed line. And the red and black curves here is what we extract from the small angle X-ray scattering. So we have a very good fit to that data. We can also, from the anomalous component, extract a correlation length through the Ornstein-Zernicke relation. And I will come back to that at the end of the talk, because that was requested before. Now, what about simulations? Well, if we want to simulate a small angle X-ray scattering going to small q, we have to have a very big box, because we're going to take the Fourier transform of the atom positions in the box. We also, so we use 45,000 molecules here. We also need a force field that can actually reproduce the isothermal compressibility reasonably well. The TIP4P 2005 model actually has a reasonable, it's the best model actually for the thermodynamical properties. So we do these simulations, and here we compare directly with experiments. So at 5 degrees, we have a perfect match in terms of the shape of our computed Sachs data. However, we do have to shift the curve a little bit to match the match quantitatively. When we start to supercool, so here experiment going down to 263 Kelvin, then in the simulation we have to cool down to 253 Kelvin. So we have to cool down more. Going even further down to 258 Kelvin, we have to go down almost 20 degrees more to have the same type of fluctuations. And when we are at 252 Kelvin experimentally, we have to go down to 230 Kelvin, and we still underestimate the fluctuations in real water. And here at 230 Kelvin, this is the maximum in this model. We are at the Widom line of the model. This has been discussed very much, so I'm not going to say too much about it. But the widow line is the extension here. This would be the picture that we also arrive at based on the experiments and the combination with simulations. So that there actually is a critical point in a liquid-liquid transition between a high-density liquid and a low-density liquid. The fluctuations that we see at ambient conditions, biological conditions, would be due to the vicinity of the widow line and the critical point here. But in order to experimentally say something about this, we need to go deeper in temperature. Here's a comparison now of the isothermal compressibility. Now, it has been measured for real water down to about 250 Kelvin about. When we look at the simulations here, this is TIP4P 2005. We underestimate the fluctuations. Here we hit the widow line at 230 Kelvin. And after that the fluctuations decrease, and they decrease because it becomes more and more dominated by the other component, the low density liquid. Now, if we take another model, the SPCE, it has a much flatter maximum down here. So here's the widow line at ambient pressure for SPCE water. Now, the enhancement will depend on the vicinity of the critical point. How far away, at the critical point, we would have a strict divergence. Now, the critical point for TIP4P 2005 water is at 1.35 kilobar, but for SPCE, it's at 2.9 kilobar. So we have a much smaller enhancement for SPCE, much bigger for TIP4P 2005. But where will it be for liquid water? Do we have a divergence, or will it bend down? In order to see that experimentally, we need to go into no man's land. And the way to do that is to, the reason that one has not been able to do experiments in no man's land is that the measurements take too long. The water crystallizes before the measurement is over. So you need a fast measurement technique. What we have used is the X-ray laser at SLAC at Stanford. This is the first X-ray laser. It's a free electron X-ray laser. And it gives fully coherent pulses of X-rays, very, very intense, and very, very short. So you can do down to 5 femtoseconds. What we do experimentally is to generate small micron-sized droplets that fall in vacuum. As they fall in vacuum, they cool through evaporation. And they cool very rapidly. They are hit by one of these pulses, and from individual droplets, we get a full diffraction pattern. We can distinguish if we have liquid water, then we have the water ring, the rings, or if we have crystals in the droplet, we get Bragg peaks. As an artist picture of the experiment, so here we would have a 12 micron droplet that falls and is hit by a 3 micron X-ray pulse, and it's generated by a machine which is 1 kilometer long, so this is really shooting with precision. Here's the data. So here's the travel time in vacuum in milliseconds. Here's the temperatures we achieve. Here's the temperature of homogeneous nucleation. And we do go below that down to 227 Kelvin. Here's the fraction of shots that contain ice, respectively water. So we see no ice crystal until we are well below the temperature of homogeneous nucleation. But even at 227 Kelvin, we still have a fraction of the order of a few hundred droplets that have remained liquid at 227 Kelvin. So what can we extract from this? Well, first of all, we need to verify the model. What we have at the higher temperatures, the measurements can be done at the synchrotron, where we can measure the temperature. At the lower temperatures for the droplets, we need to use the Knudsen evaporative cooling model to divide the temperatures. We have a very good overlap between the directly measured temperatures and the Knudsen model in this region, but down here we turn to molecular dynamics simulations to verify the model. So what we do is we simulate a water droplet. Every once in a while, water molecules evaporate from the droplet. In the simulation, we can measure the temperature. And that's a green curve here. Now, to apply the Knudsen evaporative model, we only need thermodynamic quantities. These we can define from the simulation for this particular model. And then when we mathematically model, use these quantities in the model, we have a very good fit. So the data that we're going to look at will be the structure factor. So this will be the normal structure factor measured out to 16 inverse Ångström. But the detector that we have can only cover this range. So this is what we will look at, these two first peaks. Here is the full temperature series. So in this region, at the higher temperatures, we have synchrotron data where we can measure the temperature. Here we have the droplets, and here we have an overlapping region where we have data both from droplets and from the synchrotron. So we have a very good overlap. We have a continuous development of the peaks. So they become sharper and sharper, and they separate from each other. So these two peaks we call S1 and S2. We can plot their position as function of temperature. And we have a continuous development of the liquid structure towards that of low-density amorphous ice. We want to characterize, we want to extract more information from the experimental data. So we want to be able to say something about the tetrahedrality. We need some parameter, and what we will use is the height of the second shell, which we will call G2. Here are experimentally derived pair correlation functions for high-density liquid and low-density liquid. This is from neutron diffraction data by Ritchie and Soper. So the high-density liquid is characterized by a collapse of the second shell, and molecules also from the first shell have moved into the interstitial region. There's very little contribution here. Now this position corresponds to the distance between the nearest neighbors to this molecule. We can take this from the simulations. From the simulations we can derive the pair correlation function. From the pair correlation function we can calculate the split between the S1 and S2 peaks. And this gives us a calibration curve that we can apply to the experimental data to derive a G2 parameter from experiment. And this is what we find. So here's the experimental data. Here's TIP4P 2005, which underestimates the accelerated transformation that we see in the experiment towards a tetrahedral liquid. Up here we have low density amorphous ice, and it goes towards a much more tetrahedral liquid. Now, I say towards a tetrahedral liquid. Well, people normally speak of ambient water as tetrahedral. Here's the pair correlation function for ambient water. Here's the pair correlation function for low density amorphous ice. And here is TIP4P 2005. It's a simulation at 220 Kelvin. And 220 Kelvin is where we have to go in the simulation to correspond to the G2 of the experiment. So, what we have now is we've actually gone down to where the rhythm line should be, and where some models predict that strong things would happen. We see a continuous change in the structure, in the tetrahedrality. It's accelerated when we come close to the temperature homogeneous nucleation. It's much more dramatic than we see from the simulations. And our picture here is in terms of two normal liquids. We have, at high temperatures, a pure, high-density liquid, which behaves perfectly like a normal liquid. So cooling gives an increase in density. At very low temperatures, again, we have a liquid that behaves like a normal liquid, a low-density liquid. But the anomalous behavior occurs in the transition between these two. And that's where the anomaly is. It's a very simple picture. So, it all favors this. I don't have much time. You've seen this picture before. So let me just say something about correlation length, since that was brought up. From the small angle X-ray scattering data, we can extract an anomalous component. Now, what we do here, since we're not focusing solely on the extreme small Q region, but we also go up so we can see the tail of the first peak in the structure factor. This means that we can fit a normal component and an anomalous component. So we can extract the correlation length according to Ornstein-Zernike theory. Here are the data for H2O, for D2O, and for a solution of 1 molar solution of sodium chloride. We can fit an apparent power law to the correlation length. And where we use the temperature 228 Kelvin, similar to the isothermal compressibility and CP. So it seems that even in the correlation lengths we have a critical behavior. But also that for D2O we would be closer than for H2O. And the reason for this is that the hydrogen bond strength for D2O is enhanced over that of H2O. In fact, for a mixture of HDO and D2O, for instance, we would see, and we see this experimentally from X-ray emission spectroscopy, we see HDO more preferentially in the high-density liquid rather than in the low-density liquid phase. And we can discuss that afterwards. Now, the other aspect here is that the correlation lengths are very small. They're of the order 2 to 3 angstrom, so how can that be important at all? Well, one has to remember that in Ornstein-Zernike's theory, what one looks at is the first term in the asymptotic expansion going to small q. So the correlation length in real space corresponds to the asymptotic behavior at large R. And that, oh, I'm sorry, let me go here. And that corresponds to this exponential decay. Now, to make sure that we are looking at the right thing, we have now simulated the liquid gas critical point. Even here, the correlation length is small, 5.9 angstrom. But we have a very good description of the asymptotic behavior of the pair correlation function, as Ornstein-Zernike theory would say. So what does this correlation length mean, then, 5.9 angstrom? Well, if we look at the simulation box here, and this is now 100 angstrom, so this is to scale, we see that 5.9...
The chemical charge on the polymer is enough high, there is a threshold, and of course there is an instability, and to avoid this instability, some contrails are condensed onto the macroelectrolyte. Also, you can classify this polyelectrolyte, so chemists classify the polyelectrolyte as polyanion and polycations, but for physicists, you have to compare. It's more important to compare weakly charged polyelectrolytes and highly charged. Anneal polyelectrolytes and quench, we will see what that means. And hydrophilic with respect to hydrophobic. Flexible with respect to semi-flexible. Linear with respect to branch architecture. And saturated with respect to conjugated. Normally, all the red color correspond to what I would like to present you. So if I take the example of the sulfonated polystyrene, which is the main example of polyelectrolyte, is the highly charged polyelectrolyte. You know, here you have the phenyl in the gamma position. Here you have replaced the hydrogen atom by this SO3 minus ions, and you have a quintrions, and the quintrions could be monovalent or divalent, and you have different monovalent quintrions which can be used, you know. Some quintrions can be deuterated, that is important for neutron scattering, and the macroion can be also hydrogenated or deuterated. The degree of sulfonation is quite important. It is the chemical charge fraction. And this chemical charge fraction, because it is a quenched polyelectrolyte, is controlled by the chemistry. So here, when you put the charge along the chemical sequence, of course, that's the work of the chemist, not the work of the pH of the solution. So you have no fluctuations. And also the distribution and the charge fraction is fixed. Also, you can see if on this example, these monomers, the sulfonated monomers, is soluble in water, but the parent monomer, the styrene monomer, is not soluble in water. So if you vary the degree of sulfonation, of course, at low degree of sulfonation here, until 30%, the polyelectrolyte is insoluble and is perfectly soluble after. But of course, it is only hydrophilic when you have 100% of sulfonation degree. If you reduce this sulfonation degree, you introduce some hydrophobic effect. So it is an example of a hydrophobic polyelectrolyte, a quench one, if provide the sulfonation degree is less than 1. Okay? It is important because you have also some anneal polyelectrolyte. In this case, the distribution of electrical charges along the chemical sequence is fixed by the pH. Usually it's a weak acid. We consider a weak acid, not a strong acid like here. And for carboxylate groups, for example. And in this case, of course, there is some fluctuation in the position of charges. And this fluctuation could have some importance. They are not important when you are in the hydrophilic regime, but when you are going towards the hydrophobic regime, when you reduce the electrical charges and you increase the hydrophobic effect, in this case, the quench and the anneal polyelectrolyte behavior are distinct. We will see, I hope. Of course, here, there is another point, of course, it's an hydrophobic polyelectrolyte. Why? Because if you have an hydrophilic polyelectrolyte, of course, when you increase the chemical charge fraction here, in this case, you have an effective charge which is proportional, which is directly equals to the chemical fractions, until a certain threshold, a certain chemical fraction. Beyond this chemical fraction, due to the condensation of Coulomb ions on the macroion, the effective charge does not change. Okay? If you have an hydrophilic polyelectrolyte and purely hydrophilic, when you change the chemical charge fractions beyond the Manning-Ozawa threshold, you have always the same effective charge. But you see that when you have an hydrophobic one, it's not the case. Okay? It's not a plateau here, but you have nothing until a certain, it is here, after 30% for the degree of sublimation or the chemical charge fraction. In this case, you increase slowly the effective charge. That's an important thing. For the small angle scattering, of course, the previous speakers has described some things, you know, but it's very easy. What you are measuring with this technique, it's you have a detector. I only consider the static scattering, and you measure the scattered intensity here, so the number of scattered particles at different scattering angle. Okay? And when you are in the static approximation, so you assume that there is no energy transfer in between the radiation and the matter. In this case, you have the difference in the wavelengths of the direct beam and the scattered beam is defined by something which is close to the Bragg law, you know? So what you are measuring is the scattered intensity. Practically, you measure the scattering intensity versus the scattering angle, but of course, the parameter which is significant, which is important, is the scattering vector, or Q, and this scattering vector is, of course, proportional to the scattering angle if you are at small angle. And because I am considering large particle in the red space, I will observe small q values for small angle. Okay? The formalism of this technique is very simple. It's the linear response theory. You know, you measure some correlation functions, some correlation function of the density. I will make some comments. The previous speaker speaks about density fluctuation, but me, I will speak about concentration fluctuation. So, at small angle, for example, you can neglect in the first approximation the density fluctuations, but you have, if you have a solute in a solvent, you have the concentration fluctuation. And this concentration fluctuation gives you information about the structure. I would like to emphasize also that because the polyelectrolyte has two components, of course, you have three distinct scattering functions. One for the macroion, or the blue particles here, the monomers, and you have the same for the contour ions, and of course you have the cross term. Okay? So from these partial scattering functions, depending on the technique that you use, you will see mainly, for example, the macroion. That is the case if you use the small angle neutron scattering. But if you use small angle X-ray scattering, you will see both the macroion but also the contour ions. In any case, with the small angle neutron scattering technique, you can also use the contrast variation method, which is very easy. You use the leveling by replacing hydrogen atom by deuterium to change the factor here, the contrast length of the macroion with respect to the second, or the contrast length of the contour ions with respect to the second. Of course, if you, for example, if you use the deuterated macroion in D2O, you have a chance, and if you use also hydrogenated contour ions, you have a chance to observe only the contour ions. Of course, from this partial scattering function, you could also have some information about not only the density or the molecular structures, but also the dielectric structures. So you can also extract what we call the theoretician call the charge structure functions. Finally, here, you see that you can have, for each partial scattering function, of course, you have intramolecular terms, so the correlation in between, for example, the monomers inside one chain, but you can also have the intermolecular terms, so the correlation in between monomers belonging to two distinct chains. Okay? I give you an example. Here you have the scattering from the polyelectrolyte solutions. If you have no added salt, you will observe a maximum there. If you added salt, of course you screen the electrostatic interaction in between the monomers and in between the macromolecules and the macroion. In this case, this peak disappears. Okay? If you have a neutral macromolecule, if you increase the concentration, of course you increase the intermolecular term, but you have never this kind of peak. It's only due to the long scale of the electrostatic interactions. But to observe this maximum, which is characteristic of polyelectrolyte solutions, you have to avoid any added salt. So, here you have the first result. If you have, you look at the scattering intensity versus the scattering vectors, you have this maximum, and of course the position of this maximum changes with the concentration. But not only with the concentration. But of course, that has been observed for the first time by these two persons, Coton-Mohan, and everybody has seen this maximum now. So, but the first explanation was given by De Gennes. And you know, when you are in a dilute solution, of course the monomers are well separated. In this case, of course, this maximum has something to do with the position order. So, if you want, if you take the position and you take the inverse of the position of this maximum in the Fourier space, you obtain the average distance in between the macromolecules. You have a position order. But when you are going towards the semi-dilute regime, so when the macromolecules begins to interpenetrate like that, like my fingers, like that, you know, you see you have a sort of temporary network. In this case, there is no position order, but you have some mesh size of the network. This mesh size is the correlation length, and of course, has nothing to do with the position order. It's only like what we call the correlation hole. So, around one macroion here, there is some volume which is forbidden for another macromolecules. It's like the art sphere. If you put art sphere on the, you have a peak when you increase the concentration, but this peak does not move because it's related to a correlation hole. But in the case of the polyelectrolyte, of course, this correlation hole, the volume of this correlation hole, the volume depends on the concentration. Why? Because it depends on the ionic strength, it depends on the Debye-Scaling length. Okay? So when you change the concentration, you change the position, because the correlation pole its volume changes with the concentration via the device screening lens. Okay, so you see you have a peak, but you have no order, no translation order, no orientation order. You have a perfect disordered system. Now, of course, by the position of this peak, you measure what we call the screening lens, but the screening lens has something to do with the device screening lens with some aspect. So now, if you look at for different macroions, different counter-ions, and you plot this position of this maximum with respect to the concentration, you see you have some dispersion here. Of course, the theoreticians have proposed some scaling law approaches, and specifically Dominique Colby-Einstein has proposed this value, this relation in between the screening length correlation length and the concentrations and the effective charge. Okay? So we are able to compute the effective charge for any polyelectrolyte, assuming the Manning-Ozawa condensation model. And when you do that, you compare the, yes, of course. If you compare here, it is the position of the electrostatic peak versus here the concentration, and there is a dispersion. If you replace the concentration here by the screening lens here, so you have some universal law if you want. Of course, I am sorry, but it's a problem of the PC, not the Mac. Here, so you see that the scaling law proposed by Eugene First and by Dobrynin and co-workers works. There is some, of course, there is again some dispersion. Why? You could, you could understand that first, the form factors can have some influence on the position of the peak that you obtain from the total scattering function. For example, here we have performed different experiments, and for the red one here, you have the contrails which is hydrogenated, and and the macroion which is deuterium. So when you are in D2O, you see mainly the contrails, and when you are in H2O, you see mainly the macroion. And you see that at small concentration, if you compare the scattering, the partial scattering function of contrails and macroion, the peak is reasonably at the same position. But if you increase the concentration, you have some differences. Another problem, if you want, here. So you are able to measure the effective charge by the position of this electrostatic peak. That is demonstrated here. Here we have used mixtures of monovalent and divalent contrails. That is very simple. You mix two kinds of salt form of styrene sulfonate, polystyrene sulfonate, and you obtain a change in the contrails. The contrails are either here for this variable 0 here, you have mainly the calcium contrails, and here you have mainly the sodium contrails. Of course, the condensation is not the same, so the effective charge is not the same for monovalent and divalent contrails. I don't entry in the details, but you see that, of course, you expect some figure like that from the Manning-Ozawa. Because when you mix divalent and monovalent contrails, first you condense the divalent. Okay? Here you see the maximum at small concentration is almost the same shape of the curve, you know, because here we plot the position of the maximum versus the x value, so the proportion of monovalent contrails. Of course, nothing is perfect, so here you see, you have, I don't know what, that. Sorry. Here you see when you increase the concentration, here, the shape of this curve, the Q star versus the fraction of monovalent trials, changes. And that is cannot be explained by the Manning-Ozawa model, because the Manning-Ozawa model proposed some strange curve like that. But you can explain that using another model, a mean field model, a mean field which is the Poisson-Boltzmann. And if you solve the Poisson-Boltzmann equation to obtain the effective charge, you will obtain that. You see, and with the concentration, the curve initially in the limiting law of Manning-Ozawa, you see it's very smooth. So you have this problem with the concentration. In any case, you don't explain all by the Poisson-Boltzmann equation and theory, of course. It's only the mean field theory, so you cannot explain all. But you explain something. So you see, from the Manning-Ozawa model, there is no agreement in between the theory and experiments, and with the Poisson-Boltzmann, it's also, I would like to emphasize that if you compare the acid form of the polystyrene sulfonate and the salt form, you have a change here on the effective charge. I don't want to go into details, but of course, if you consider the proton, the Coulthard H+, it is more condensed than the Coulthard sodium or even the Coulthard cesium. That it's probably due to not only the ionic radii, it's probably due to some also hydrogen bonding. No, and that is an agreement. So you see here, I am in the dilute regime. The Q star vary like C to 1/3. Then I go in the semi-dilute regime. Q star vary like C to 1/2. If you are in the concentrated regime, you have Q star which vary like C to 1/4. That, I don't explain that, but it's very easy to explain. In this case, the thermal blob, the electrostatic blob, corresponds to a certain concentration. You can assume that the macromolecule is almost Gaussian. But that regimes, each regime is characterized by a scaling law. It's very simple. You have an exponent which characterizes the regime. And you see that this free regime here, dilute, semi-dilute, concentrated, was well described by theory and also has been relatively observed by the experimentalists. And when you go beyond the concentrated regime, when you increase the concentration, when you go to the melt. In this case, you have the case of the swollen regime. The swollen regime has been proposed by Nishida first. And I would like to discuss that now. Why? I would like to discuss the existence of an orientation order in polyelectrolyte solutions. Until now, nobody has observed any orientation order with flexible polyelectrolyte, for instance. But normally, if you have anisotropic particles, like that, you have at low concentration in isotropic solutions, but if you increase the concentration, you have some compactness arguments, which lead to some orientation order, like that, elegant, like some symmetric liquid crystal. But to go from isotropic to the nematic, if you want, regime, you have the Onsager transition. Onsager has predicted that in 1949. And all has been observed with the virus, the tobacco mosaic virus, by Kepler, and also by some bacteriophage, by Fraden and Grenet, and also by some short DNA. Okay? And what happens when you consider low polyelectrolyte, but with some local stiffness. That is my problem. So I give you a summary of that because I'm not sure that I can go until the end. Well, you see, I will tell you that I want to emphasize the importance of the intrinsec stiffness of polyelectrolyte. The behavior of the polyelectrolyte peak is the signature, the fingerprint of the regimes, of the structure. So you have these two regimes, which has been observed in the past, and that, of course, if you use another polyelectrolyte with an intrinsic stiffness higher, in this case you observe two other regimes. Q star very like C, proportional to the concentration, and after it is proportional to C to 1R. So here you have two regimes which are distinct of what was predicted before by theoreticians and even by experimentalists. And of course, this regime, Q star proportional to C, is like a metastable regime. You know, at high concentration, you observe some nematic phase. You can observe some birefunctions, but in fact, in between cross-polarizer, you are not able to observe any texture, classical of nematic phase. It's because the domains are very small, I think so. But you see a small birefunctions, and you observe the Q star, which very like C to 1R. But just before, you have the mixtures, and of course, it's like a metastable phase. It is a jam random close stacking of equivalent solid rods with the length comparable to the length 160 lengths. So you see, I would like to emphasize that this nematic phase was predicted by Mirkova and co-workers, and also by Karim Tukumar, but they only predicted this phase. They have not predicted this quite strange regime where the maximum is proportional to the concentration. So, we have used different polyelectrolytes with different intrinsic stiffness here. For example, here for the polystyrene sulfonated, you have 10 angstrom for the naked persistence length. If you go to the polydenmark and other polyelectrolytes, polycations, you have 30 angstrom. And if you go further with the hyaluronate, for example, you have something which is twice the polydenmark. So, I give you some small angle X-ray scattering results here. So you increase the concentration, so the peak moves here. It is the electrostatic peak. So when you increase the concentration, because you increase the ionic strands, of course the peak disappear when you increase the concentration. But at a certain concentration, you have another peak. It's always a correlation hole. This peak here is much more a steric correlation hole, not an electrostatic correlation hole, if you want. And in this case, you can see that, of course, that could be, there is another behavior. It's not so easy, but you have another behavior, you can see. At high concentration, you observe what Nishida has observed before. So you have some ionomer regime. I don't want to speak about that. So you see, you observe C to 1/2, C to 1/4, and after something which is a pure ionomer regime, because you have decreased the electric constant of the solution, of course, and so you have dipoles here, and you have some association between dipoles. But you know, when you know, now if you use polydenmark, you have the same, but the contrast is lower, of course. And what you are able to observe, you observe the semi-dilute regime as well as you will see with the small angle neutron scattering, but you see you have this Q proportional to C here, and after the nematic regime. How you can explain that? Of course, I consider only the excluded volume between two rod-like molecules here. And the distance here, the excluded volume, is proportional to the length of these objects and to the diameter of the cross-section. But here, the diameter corresponds to the closest distance on approach, so it corresponds to C, not zeta, C. And the compactness imposes this relationship on this one. So if you have this geometry here, you have this closest distance of approach, which is inversely proportional to C. And when you consider this, you have, which is proportional to the inverse of the square root. So you see, when you have electrostatic, this configuration is the most probable configuration, of course, because you have a strong vibration. If you consider the compactness, the Onsager problem, of course, the best configuration is that. So you see with polyelectrolyte, you have some frustration in between these two interactions. So, of course, when you increase the concentration, the electrostatic interaction decreases, of course, but you have this combination of the electrostatic interactions and the compactness argument of Onsager. And that is why you explain, you observe this metastable regime in between the concentrated regime and the pneumatic phase. And you see, in this case, you don't observe any ionomer approach. I finish 1 minute, sorry. Here, there is a comparison in between results obtained by small angle X-ray scattering and results obtained by small angle neutron scattering. It's quite interesting because, well, my knowledge, is the first time that I see the influence of the labeling of the contrast on the intermolecular term, not on the intramolecular term. Usually the effect is on the intramolecular term. But here it's an effect on the intermolecular term. And it's only related to the fact that the contraions are much more mobile along the polymers. And when you consider the contraions, of course, the excluded volume is reduced. So the position of the maximum is not at the same position that if you look at only the macro wind. Okay? I finish once. If you put salt, if you add salt, in this case, you suppress the electrostatic interaction. And you see that if you suppress the electrostatic interactions, of course, this regime, Q star proportional to C, disappears. You favorize the pneumatic regime, of course, because you kill that. You have only that. Thanks, I finished here. I'm sorry. Here you see, okay. I will stop here. You see, with the hyaluronide, the contraions, there is no, if you want, you have no condensed contraions. And in this case, if you use X-ray, you see only the macroion, because the contraions are in the solvent. And you can compare that with the polydenmark, but in the case of the polydenmark, you have to use neutron to observe only the macroion. Okay? And when you compare that, you see, of course, first, the regime, the jam regime appears when you obtain the Q star close to the persistence length, but you see also that you observe the difference in the persistence length, the naked persistence length, so the persistence length, the non-electrostatic persistence length of the two polymers. That's all. I'm sorry. Thank you for your attention.
That is open for discussion. Question, please.
You're welcome.
Yes, you state correlation code. Yes, can you a little bit please explain
Of course, if you have neutron polymer, you can observe some Onsager condition. I only show here that if you have polyelectrolytes and flexible, semi-flexible electrolyte, if the polyelectrolyte is too flexible, in this case, you have no Onsager condition. If the polyelectrolyte is very stiff, you observe Onsager condition. That is the example of the bacteriophage and even of tuberculosis. But, of course, here when you have semi-flexible polyelectrolyte, the electrostatic involved, you observe this jam regime only because you have competition in between the electrostatic, which favorizes these configurations, and the contact press, so the Onsager condition, which favorizes this parallel configuration. With an equal electrolyte, you are not that. So you will not have this metastable phase if you want.
Correlation pole. Can you go correlation pole? You remember you told us what correlation pole?
The correlation pole, for example, if you have a particle here,
Yes, I understand. It's like you have to talk, you cannot like throw another particle in this.
if you have art sphere, for example, the correlation pole you cannot interpenetrate. So it corresponds to the bubble of the radius of the sphere. It is a volume, which is forbidden for the other particles.
Actually, it's like
And there is no other, I insist about that. You know, if you have some ball on the table like that, you have no other, but you have some peak. If you increase the concentration, you will observe a peak, and this peak has nothing to do with any position of it.
And as an
Yes. As far as I understand, according to your point of view, the proton is the hydrated proton is bound better as compared with sodium ion to the sulfonate polyelectrolyte. Yes?
Yeah.
But
Why? I don't know precisely.
the ion exchange constant between these two ions on the surface of ionic surfactant micelles is close to unity. So is really such a difference between ionic micelle surface, so first
I think
sulfonate
that
and
it's a difference
the
between
polyelectrolyte?
electrolytes and
Yes?
micelles, if you want. I don't know the case of the micelles, but it's clear that if you compare different monovalent neutrons, usually you have no difference in the position of the Q star with respect to the concentration, because you have almost the same effective charge. Almost the same. There is no, what is the name of this crazy biological effect. But if you take the hydrogen, if you take proton with respect to the monovalent neutrons, in this case, you have a change in the effective charge. That's an experimental result. I don't know, I have not looked for to understand more, but I think that that could be related to the ionic radius, but it's not enough. You cannot explain all by the difference in the ionic radius of the neutrons between sodium and hydrogen. My only explanation is that you have some additional bonding, H bonding effect. That's all.
The sulfonate group stayed unprotonated, yes?
Is liquid. Some are called solution lines and called pressure. The topic is transformation and fluorescence is in copper alloys. I intend the in materials phenomena. I introduced the off-shape copper-based shape. Peculiar return to a shape or dimension subjected to temperature created by the and caused by in decay and based on my shape of the plastic developed temperature market recovered the means on heating position temperature. material side, deformed and cooling, and the two kind of shape of irreversible. One reversible. The mechanism of its base measurement of the material, low temperature, and open coil. On cooling, but austerity into the martensonic level. Of the condition heating to the shape of the after cycle two-way shape of in the one-way shape the material for the default shape cooling. Reverse shape the return shape under the and on heating before the and the default shapes heating. Shape of the materials is a microstructural chain or Armstrong internal stresses change occurs in or bulk level. Transformation occurs in thermal manner by temperature parenthesis characterized by the structure of material transformations and fast transformation in martensite movements over the short distance order of by means of shifts. There's cooling on cooling in martensites or the martensites applied stresses temperature conditions. This are schematic as program. High temperature structures are ordered into the determinant and with different martensite, the different martensite. And the stress turn into the parent phase into the in effect. Ordered turn into the side on cooling the martensitic temperature. What is first order transition and occurs with the protons in this decimal or there's transitions. Characters, product martensite inherits the and austerity phase. The transformation makes in better areas which exhibits the first one is distortion and the second is invariant share. Better phase structures, basic body structures, this is in caloric type, also type unit type unit is a which an expansion 26 to the type of suspension or 11 to the 1 and or type direct FCT cell as a first beta phase structure phase cell corresponding FC structures. Therefore, the FCT units and FCC being basic structures and with FCT turn into the S-centered. Notice even in homogeneous martensite variant 1-1 type matrix, which is both martensite. Invariant shows opposite direction, 1-1 type direction, 1-1 type in the 1-or direction along type shares cause direct structures. 1-1 type basal plane structures of an area with sequence called 3R9R depending on the brush bucket ordered. The periodicity set is through 18 directions that in our direct structures and of structures is schematic. This layers of phase one better phase and less layers structure cooperative out of schemation. This is also present copper alloys also this critical transformatures are room temperature. Auto alloys in the current condition, the room then from those alloys for homogenization of phase field as current in an aged at room temperature. Aluminium and alloys are 834 degrees. Copper, aluminium. Further specification were filling the alloys and were sealed was and even treatments. Homogenization is keeping at is for copper aluminium. It 700 minutes and current grade. Different programs specimen evidence of aging term in this is a factor of aluminium alloy. It's exhibited that this has the order in the marxistic peaks for trans explanation of acidic transformation. In particular, great importance. Of copper alloys aging is about series programs have been taken from alloy samples in a time interval and have been peak characteristics with, in particular, the success toward the success provide relations and for 18 as listed as follows in our structure X-ray program. That's phase 208, 1 or 3 at the long term is 10 years. It is less peak phase on the phase aging with chance you will banks in the crystal of recently atoms in marxistic condition. Whether Pilates 1-1 is subject to torsion with participation. Atoms are important effect. The atoms of size of martensite regular hexagon. The deviations of arrangement of in case are different. Disordered case, all of sides are randomly side and atomic approximate each other. Ordered case, sides are popularly by atoms, which have atomic size deviates from the hexagonal arrangement of the atom size differences. Yes, if the basal plane of the years with Martin's transformation, the disordered case, atom sizes acquire age, and in this the hexers is regular in the occupying the last are different. In this case, the hexers from the hexagon electron diffraction, but also the superlations. Only shapes evaluated ions in microscopes of martensite. The fundamental beta type martensite from the closed bucket, which consider closed bucket type martensites have structures and are in the stacking on the order. Copper-based diothermic types and following stacking occurs with A, B, C, A, C, A, B, A, C, A, B. Only the speculation for 9R or 8 originates from one island, one beach, and it occurs in operation during the Bazar contain or connected to the exercise formation one important way of sizes can be taken approximately by therefore this survey can be the ordering site. Martens undergo the sorting reaction contrast in the Martens region. Disordering occurs as transition and in the unitless aging. Particular infusions occurring in the particular community, diffusion because this is as structure. This also is the of atoms in this. Thank you very much. Liquid, it is.
But really interesting can be the sample which property of memory shape that in connection with storage. Was which smallest size of machine and the property. This because it is in effect and you simple reason for
Is based on formation crystal.
okay, but make a sample for instance thousands of atoms, will it still have
According to the material, the size of
so it is possible.
because I is the physical basis. These are most engineers artifact.
Thank you.